Could we get everybody to take their seats, please? Thank you. I'd like to thank everybody for coming today. There will be a few housekeeping items I'll go over in just a few minutes. But we do have the chairman here, Chairman Julius Genachowski, to give a few opening remarks to get us started.
Thank you. Was that my introduction?
Yes, it is.
Thank you very much. And I appreciate the introduction. I particularly appreciate being here, and I especially appreciate what this workshop is about. First of all, let me thank some people who worked very hard to organize it. We had staff in our wireless bureau, our Office of Engineering and Technology, Tom Wheeler, the head of our TAC, our Technology Advisory Committee, obviously worked very hard on this. He could not be here today, but we do have members of our Technology Advisory Council here. When I appointed Tom to lead the TAC, I said I wanted a group to focus on real things, not to be a debating society, but to take this wonderful opportunity of us having assembled a mixture of people with incredible experience from the private sector and the academy, with real business and technical skills, and put those minds toward helping us solve some very concrete challenges the country has to move our broadband opportunities forward, to move our broadband economy forward, both in the near term and the long term. There's a lot of good news in our broadband economy, and the last few years have been a real success story. We've now regained global leadership in mobile. Several years ago, we were all talking about how some other countries, South Korea, Japan, were doing all these incredible things on their mobile devices. We were talking about how Europe was ahead of us because they were texting and also doing things that in the U.S. people hadn't started doing. Well, flash forward to today, everyone around the world is using American operating systems, American apps. In fact, here's an interesting statistic. The percentage of global mobile devices with American operating systems has gone from under 20% to over 80% in just 4 years. And as you all know, we are on track to lead the world to roll out a 4G LTE at scale. We have 69% of the 4G LTE subscribers today, making the U.S. The world's testbed for 4G LTE. And we also continue to be the leading country in the world when it comes to unlicensed use, particularly Wi-Fi. More hotspots than any place in the world, and real innovation around unlicensed spectrum, including white spaces. Some of it I expect to come to market in the near future. Now, for all of that good news on the wired side, too. 4 years ago, the percentage of Americans that lived in areas where there were networks capable of providing 100 megabits or more was 20%. Today, that number is 4 times as much, 80%. So we're making real progress as a country in our broadband economy, and we see that around us because investment is up, innovation is up around the broadband economy, both networks and infrastructure, wired and wireless, and also all the apps and services running on devices. Now, for all the good news in the broadband sector, of course, there are some very real and significant challenges ahead. This is a fast-moving area, as you all know, and the challenges remain significant. In fact, our successes are producing some of our most significant challenges. And so we have this, wonderful demand for high speed, which is incentivizing remarkable innovation on our broadband networks. Well, we need speeds to continue to go up and up and up, and capacity to go up, we need to have a world of broadband abundance to maximize the incentive for innovators to continue to innovate. And just as over the last 5 years, our incredible innovators in the United States have invented things that we never would have imagined 5 years ago. If we keep on pushing on the gas on broadband speeds and capacity, that'll happen again. And then bringing us closer to the subject of this workshop, of course, our success around mobile is creating enormous challenges. As you all know, demand for spectrum, the demand for data from smartphones and tablets is increasing exponentially. And so your smartphone produces a data stream that's not 10% or 50% or 100% more than the phone that you upgraded from. It's 24 times more. Your tablet is producing a data stream that's 140 times more. Well, this is it's a surprise. It's a wonderful surprise. You know, people weren't sitting around 6 years ago and saying, "Hey, let's assume a world where data capacity is growing at an exponential rate for as far as the eye can see. Let's talk about what kind of spectrum strategies and policies would deal with that." But that's the situation we're in. It's a very real challenge. It's the kind of challenge we want to have because it comes from too much demand. Believe me, much better than the opposite. But here we are doing one of the things that we need to do at the FCC together with you to try to tackle these challenges. And the specific focus of this workshop, which I'm very excited about, is band plans. Band plans are exactly the kind of issues that our Technology Advisory Committee should look at. It is, I will tell you, that the ability for the TAC to have concrete input in thinking about how the FCC should do band plans in this new world, the opportunity for impact is very, very significant. We are going to be listening very closely to what happens at this workshop and what comes out of the TAC process in terms of directions and recommendations for the FCC. What are band plans? Many of you here know, and some of the people listening may not. When the FCC is able to get a block of spectrum, it has to decide how to allocate it. And typically it divides that spectrum up into pieces and sets some rules around the different pieces. And then the entities who are using the spectrum use it in those ways. The thinking on band plans is, let's just say, still in the same order of magnitude where it was when the FCC first started doing band plans. There have been some changes, of course, but we're still kind of operating in the same assumptions and parameters. Well, the world has changed, so it raises the question that I've asked all of you at this workshop to consider today: how should our thinking around band plans change? We've moved from a mobile world of voice to data. How should that change the way we look at band plans? We've moved from a world of, in retrospect, very modest capacity demands to one with much greater capacity demands. How should that change how we look at band plans? I suspect in your process you'll identify other differences that have occurred for which we should optimize as we develop band plans. Now, this is, of course, not a strictly theoretical exercise in the sense that it's not just that we think at some point in the future we'll have to figure out some band plans. We're going to have to, as a commission working together, sort through some challenging band plan issues in the relatively near future, and that is because Congress, a few months ago, granted the FCC the authority to conduct incentive auctions. As you know, it's a new mechanism to free up spectrum that's being used to then rejigger spectrum so that large blocks of contiguous spectrum can be put on the market. We have already started our work on incentive auctions. We expect to move forward with notices in the fall. This process is moving, and we're going to have to do a band plan for the spectrum that gets freed up. And so in the way that everyone for a while spoke about 700 megahertz, even though before people were speaking about 700 megahertz, they weren't. Well, very soon, everyone in this room and many others are going to be speaking about 600 megahertz, because that's where we expect to free up the spectrum, and that's where we're going to have to do a band plan. So that is near term. There's another opportunity that we hope is a near-term opportunity as well. It's the 3.5 gigahertz band, where we believe that new technologies around both small cells and sharing, dynamic access, create an opportunity to put that 3.5 gigahertz on the market much sooner than anyone had thought. As many of you know, there are exclusion issues, interference issues involving that spectrum on both coasts. The PCAST report, this is the President's Committee, I'm going to get the initials wrong, something as Science and Technology Advisors, or the President's whatever, but it's a very important committee. And one of the recommendations is that 3.5 gigahertz, because of these changes in technology, should be taken seriously and could provide opportunities for putting more spectrum on the market as a new platform for innovation. I've mentioned previously that one way to think about that band is as a small cell band. And one of the things that we've seen in our history is that when the FCC does something like that, it ends up sparking real innovation. And so we certainly haven't decided this, and this is something that we'll look at in our NPRM. But we do think the possibility will certainly raise for the community the possibility that thinking about 3.5 as a small cell band could lead to enormous opportunities and create another area where the U.S. leads the world. So that's another concrete example of where on the spectrum chart your work will have real impact soon. And by mentioning 600 megahertz and 3.5 gigahertz, I don't mean to omit any other opportunities. But I do want to emphasize how concrete and important your work is to us, that the channels for input are very, very real. And therefore, I so appreciate all of you taking your time to come here, roll up your sleeves, and help us, for the country, make progress on these issues quickly. Now, I can think of no one better in the universe to kick off today's workshop than Marty Cooper. Marty, known to a small number of people in the room as a member of our TAC, of our Technology Advisory Committee, but probably known better to 60 Minutes viewers and many, many other people, and most accurately, as the father of the cell phone. Marty, for those of you who know him, is just an incredible person with an incredible history. He has instigated enormous change in wireless communications throughout his remarkable career. It's not an exaggeration to say that Marty is a very real but-for cause of all the things we're seeing here, that if Marty didn't do what he did when he did it, the mobile revolution that's providing so much economic benefit, social benefit, to our country and indeed around the world wouldn't happen. And so I'm just, as a matter of personal privilege, thrilled to be sharing the room with Marty and introducing him. We all look forward to hearing Marty's thoughts in this area, how our band plans should develop, should keep pace with changing technology and changing markets. It's possibly Marty will come up here and lay out for us exactly how we should do our band plans in the future. Possibly he'll come up here and say that we need band plans no longer. I don't know. This isn't scripted. And that's how we do these workshops. We don't know what will come out of it. We encourage you all over the course of the workshop today to roll up your sleeves, to ask hard questions, and to work hard to help provide us answers and directions to accelerate our work. So please, Marty Cooper, the mic is yours. I thank you for coming out here from California to participate in this. Thank you all. And everyone, please, a round of applause for Marty Cooper.
How can anybody ever live up to an introduction like that? Wow. It really is a privilege to participate in opening this meeting, although I must tell you, Mr. Chairman, I would prefer to be the last rather than the first speaker, because then I'd have the opportunity of explaining what everybody meant to say during the meeting. But it's inspiring to watch what happens. And when I hear the chairman talk, I understand now the nature of the leadership that caused the TAC to be created. It's inspiring to see a group of people with disparate interests get together, some of the best minds in our industry, working hard at solving specific problems. I hope that we're setting an example for the Congress, but I'm not optimistic about that. I've been working with the FCC for most of my 58-year career. It's all been in wireless. I've observed that the FCC is probably one of the most misunderstood and least appreciated agencies in the government. Just think about it. Every time they make a decision, the losers are, of course, very unhappy, and the winners, especially when spectrum is involved, are never satisfied. And yet, somehow or other, after all the bickering, after all the contention, we're amazed at the realization of what the FCC has responsibility to do. We've been doing big things. I have had a good fortune over the years to be involved in a number of successes that have resulted from the FCC's policies, and I thought I'd go through some of those with you at this time. I've spent most of my career as a risk taker and innovator, and I think it's time for me to back down a little bit, so I have a new career. I'm now a historical futurist. The history that I talk about is far enough back so that there aren't many people left to dispute what I have to say. And the future is far enough ahead of us so that I'm not going to be accountable. I'm in the most safe profession that there can be. So I want to talk about maybe a half a dozen revolutions that have happened historically as a result of the partnership that I've had with the FCC. Now, the word revolution is used very loosely nowadays, and so I ought to define what I think a revolution is. A revolution, especially in technology, is an event that has a meaningful effect on the behavior of a significant number of people. So it's the behavior change that's important, not the technology itself. So let's go back to 1950s. We introduced push-button dialing for rural communities. Now that doesn't sound very revolutionary, but just think about the tens of thousands of people who were totally isolated previously, had no communications whatever, and now had push-button telephones where most of the country was still dialing. All these people who were isolated were now back in the real world. A decade later, we worked with Bell Laboratories, created the IMTS. Started out being the interim mobile telephone system. And it worked reasonably well. It was the first nationwide dial system. And it actually worked real well as long as you didn't try to make a phone call during the busy hour, because we had at that time a 5% grade of service. And I don't mean 5% blocking. I mean the chances of getting a dial tone were 1 in 20 during the busy hour. But it worked. Just a few years later, the superintendent of police of the city of Chicago came to us and told us he wanted to get his patrolmen out of their cars and onto the streets. Why were they stuck in their cars? It was the only way they could communicate. And so we created a system that allowed portables to work anywhere in the city of Chicago, including in their cars, so they could still patrol in their cars, but also be on the streets. And guess what the technology that we used was? It was, in fact, a cellular system. This is back in the 1960s. It had reuse of the spectrum, didn't require handoff, so it really wasn't exactly cellular. But you didn't need handoff for public safety because a public safety conversation is typically, the whole conversation typically the order of 15 seconds. But it worked. 1970s, 1971, we introduced high-capacity paging. Anybody here remember what a pager was? Well, that was a huge industry for a number of years until cellular essentially obsoleted it. There were as many as 50 million pagers in the country during the 1970s and early 1980s. And then, of course, in the 1980s, cellular started. And in the 1990s, digital cellular. Cellular was most certainly a revolution. It has changed the behavior of every person in this room, whether you have a cell phone or not. There are today over 5 billion people in the world that have cellular telephones. We're still in the early stages. The chairman talked about the advances made in this country, but most of the people in the rest of the world are still talking on cell phones. We don't do much of that anymore. We now have hundreds of different kinds of devices, thousands of applications, hundreds of thousands of applications. The content is so voluminous that we've had to invent new names to describe the magnitude of how much data we're doing. I don't know if anybody here knows what a brontobyte is. A brontobyte is 1,000 yottabytes. And a yottabyte is a number that represents today about the total data on the entire World Wide Web. But the magnitude of growth of data, as the chairman pointed out, is exponential, and pretty soon we are going to be talking about multiple yottabytes and brontobytes. So I want to talk to you for a little while about the coming revolution, and really not just one revolution, it's multiple revolutions. The first one has to do with our healthcare system. Everybody here is aware of the fact that our healthcare system is broken in many ways. We, instead of preventing disease, we cure diseases. We are essentially going broke. We're using almost 20% of our gross national product to support healthcare. That number is increasing. If we don't do something, it'll go up to 30%, and that's just not sustainable. Well, wireless technology is going to make a big impact on solving that problem. How? Suppose that instead of having an annual physical, which is essentially worthless, because you can't just make a measurement of an individual once a year and learn anything significant, suppose that you could do a physical every minute or every 20 seconds. You could measure things on a person's body and know that a disease is starting to happen before it happens. That's a picture of what the future of healthcare is going to be. We are, sometime in the coming generations, going to eliminate the concept of disease, head it off before it actually happens. What about education? That, by the way, if you don't consider that a revolution, then we can't communicate at all. How about education? We've discovered that children can learn faster and more effectively outside of school on the internet. They spend a huge amount of time playing games, but they learn from these games. My grandchildren understand how to access the internet far better than any of you that are picking this up in the later stages of your life when you don't learn as fast. So we're going to see a reversal of our educational system. Children are going to learn at home and go to school to do their homework, where the teachers can mentor them and teach them the concepts behind learning. That is going to be a revolution. Public safety. We're finally going to have a national compatible public safety system. It's going to take a long time before our public safety agencies all get together and do that, or use that system. But we will now finally be able to react to a major terrorist event or something that requires multiple public safety organizations to get together. That's a revolution. The concept of entertainment is going to continue to evolve. The biggest thing that I've heard lately has to do with glasses. Google has announced that they have glasses that allow you to have a virtual picture of a screen. Pick the size. Everybody can now have a 60-inch screen or an 80-inch screen. And the whole concept of entertainment is now changing. You don't have to go to a theater. You don't have to sit at home. You can be entertained, educated, and whatever else you do when you look at pictures while you're on the move. But the most profound, the most life-changing event that is going to happen, the big revolution, has to do with social networking. We're just getting a hint of what the impact of social networking will be on us. And the place that I see that most is in the Arab uprising. The Arab uprising in Libya, Egypt, and other countries could not have happened without social networking. How is that going to impact us? The whole concept of a hierarchical business organization is going to change over the word. And by the way, that includes the government as well. We are going to get much, much more efficient than we have been before. We are going to have orders of magnitude improvement in productivity. And what is the problem that we're solving there? It is the problem of poverty. The only way we're going to solve that is by improved productivity, and wireless is going to show us the way through social networking. So all this is going to happen. Some of the things I talked about are going to take generations. People don't adopt new technology all that quickly if it forces them to change their habit. But amazingly enough, one of the obstacles is not spectrum. Through the efforts of the FCC in redistributing spectrum, because of all the new technology that's coming, and by the way, the technology is really the long-term solution, because we don't need a 50% increase in spectrum or a doubling of spectrum assigned to wireless. We need a 20 times increase or a 40 times, and with that requirement is going to keep increasing, and the only way we're going to keep up with it is with new technology. But that technology exists. The combination of the FCC's vision and the industry's efforts are going to solve our spectrum problem. But there's a bigger problem. The challenge is not bandwidth, it's what bandwidth costs. Remember now, the spectrum belongs to everybody, and if the advantages of these revolutions that I'm talking about are going to accrue in a meaningful way, they have to accrue to everybody. And that means that the cost of spectrum, the cost per bit, of information has got to go down as fast as the cost of all our devices. Now, I think you're all aware of the law of spectral efficiency that says that the amount of spectrum, the throughput of spectrum, has essentially doubled every 2.5 years for the past 110 years or so. Well, there's a corollary to that, and that has to do with the price experience curve. The cost of delivering a bit of spectrum has dropped in half for 110 years, every 3.5 years. So that's a compounded growth of 22%, even though we've had like 1 trillion times improvement in the cost. That's still only a 22% experience curve, which is about the same as a typical piece of electronics or just a simple radio. So it's not a particularly difficult number. But that change in cost has to happen, and one of the difficulties that the FCC and the industry has to face is disciplining that situation. It's not going to happen automatically, to make sure that the price of bandwidth keeps going down. I know the FCC is sensitive to this issue. They have a lifetime broadband adoption pilot that's going on with that specific competition, with that specific goal in mind. But that's a wired broadband system. Remember that people are mobile. They're fundamentally natural mobile. So when we talk about broadband and broadband solving problems, it is going to have to be ultimately wireless broadband, and we're going to need multiples of spectrum at much, much lower cost than we have today. The chairman closed the last TAC meeting by making an appeal for actionable recommendations from the TAC. So I'm going to suggest to the TAC that they have 2 recommendations. I'm not certain that they are going to accept them, but I hope they consider them. First of all, we desperately need a national spectrum technology roadmap. We have to start looking at what is going to happen over the coming years and have the FCC have the tools available so that they can create policy that's consistent with what's happening in technology. And the other one, I know Julie Knapp is carefully listening to me and shuddering, is we have to start measuring spectral efficiency. Yeah, we are getting more spectrally efficient. I mentioned before that our spectral efficiency on the average is halving every 2.5 years. But if we don't actually measure what we're doing, how will we ever know whether we are succeeding? How will we be able to ever set goals for us so that we can continue our leadership in the world? If you think that the challenge that we faced in creating this leadership position that we have in the wireless industry today was big, the next one is going to be really enormous. Now, how can I be talking about the next one? We are just starting to implement 4G, but believe it or not, this technology is moving so quickly now that LTE is going to be obsolete in 15 years. Is that a bad thing? Not really, because it's going to be replaced by, I predict, whether my prediction is right or not, we'll find out, but dynamic spectrum access, which is a combination of all the technologies that we know about. SDMA, cognitive radio, you put all of those things together and the spectral efficiency and the cost are going to go down by orders of magnitude. But it's going to be a challenge to do that when all the spectrum has now been assigned and it's all productively creating stuff for us. So I think it's important that we have a roadmap that even today, 15 years before it happens, the FCC can be thinking about. Should we set aside elements of spectrum for experimental purposes? Should we withhold some of the spectrum from present use so that when the time comes to implement these new areas of advance, that we'll have spectrum available? So the TAC is in fact doing some of the roadmap work, and you're going to see that today. We are actually looking at what's happening with band planning in handsets for the next 5 years or more. What I'm proposing is that the FCC take the leadership in institutionalizing that roadmap, that they get other people involved, NTIA, perhaps even the national academies, and start creating a national roadmap that will let us maintain our leadership on a continuing basis. I found out last week, it was an article in the Wall Street Journal, it says the United States is 159th in a list of countries in growth of GDP, gross national product per person. Now maybe we ought to let the rest of the world catch up. This is one area where the U.S. has always had leadership, but I don't think we ought to make it that easy for them. I think that we ought to be pushing, increasing our gross national product per person at a faster rate, and wireless has the capability of doing that, but it's not going to happen automatically. I think we're going to have to work very hard at it. So, this is my view of the history and the future, but I think now it's time for us to get to work and work on the present, and that's what we're going to do now. Thank you very much.
Thank you, Marty. So now we're going to go over a couple of housekeeping items. My name's Cecilia Solhoff. I'm an outreach specialist here at the FCC. For those of you watching remotely, you can submit questions for the panelists, but there will be 3 panels with a period of question and answers afterwards. You can submit questions remotely by sending an email to livequestions@fcc.gov. And those sitting here in the audience, we have some note cards and pens on the back table where the handouts were as you came in, and we'll have a couple people walking around. You can submit your questions on note cards and pens, and someone will collect them from you. Just raise your hand. If you would please give your name and the organization you're affiliated with on the question, that we'd appreciate that. The panels today, several of the speakers will have presentations. The presentations will be posted on the event webpage at www.fcc.gov/events/forum-future-band-plans. So those will all be posted hopefully within a couple of days after the forum today. So the first presentation we're going to have is going to be from William Mueller, who is with the strategic marketing. He's a strategic marketing manager at Avigo. So he's going to give us a tutorial on filter design.
Okay, so if I push, I'm supposed to get a slide, and I'm not seeing it. There we go. Okay. Wrong presentation. The one that's up is from the panel session. Let's try it again. As usual, technical difficulties in the technical symposium. Not sure how to get the right presentation here. We're getting it. Okay. So while that's coming up, a minor correction. I'm going to be more ambitious than a filtering tutorial. This is going to try and talk about RF front-end components and their limitations in their entirety, and filtering is part of that. And the reason for doing this is context for the panel that follows, which is where are we today in terms of what technology can do, and what are some of our limitations. So what this plays into is at present for economical rollout of band plan, what makes sense relative to where we are and what's pushing the envelope and causes us to have to do something different. Okay, so in that context, what I'm going to start with is a simplified block diagram of the RF front end. This is the area I'm talking about. I will apologize up front. In our world, in my world, there are tons of acronyms, and RF is an example of that. RF stands for radio frequency. I'll try and explain any acronym I come across, but if I miss a few, please bear with me, and if I become incomprehensible, let me know somehow. Okay, so what we're looking at here is a radio, and the portion of it that is actually sending signals out into space and bringing them back in from space. And it's worthwhile to get really simplistic at the beginning and say what we're talking about here is a system that's out there for sending information and sending it over airwaves. So we have a bunch of pieces that cause it to work. We have a way to digitize the information. We have a way to impose it on a high-frequency carrier. And those are the blocks in blue on the left-hand side of the slide. I'm not going to be talking about those. Once you've done that, you have to get it out into space to the receiver, and then the receiver has to be able to take the information in and strip off the information and turn it into something useful. The components that do that are what we're talking about in the RF front end. All of these are analog components. They're not digital, so they don't follow Moore's law, and they have certain limitations but a certain amount of flexibility. There are 5 kinds of components I'm going to be talking about going across this. The first are amplifiers. Their job is to make the signal bigger. Second is filters. Their job is to restrict what's going on in spectrum. On transmit, what they're doing is making sure you're not splattering into neighbors. On receive, what they're doing is making sure you're not being overwhelmed by neighbors. Third thing is switches. Switches are just path selection, but there can be really 2 uses here. One is which frequency band are you working on, a band switch. Another is for a mode of operation called time division, it can be switching between transmit and receive. You're staying on the same band, but the way you're working is you're doing transmit at one moment in time and then stopping and then receiving. So in the block diagram, you may notice there's a lower path and an upper path. The lower path is a TD, or time division path, that uses a switch like this. The upper path is an FD, or frequency division. This is the way classically we've allocated spectrum in the U.S., where there is a block of receive spectrum, a block of transmit spectrum, and 2 filters keep them separate so they can operate at the same time. And the philosophy has traditionally been by operating at the same time, it's more efficient use of spectrum. The same spectrum is always being used for transmit and receive rather than alternating between transmit and receive. The top uses paired spectrum, the bottom uses unpaired spectrum. Okay, so switches. And then past that, there's an element that's starting to creep in, which is adjustable tuning. This is radio frequency components. Performance is highly dependent on the environment they're in, and by changing the aspects of that environment with an adaptable piece, then you can change the performance around. And so tunable elements will be talked about a bit. And then the last piece is the antenna itself. This either radiates the signal or brings it back in. Okay, so let's look at the power amplifier in a little more detail. What we're concerned with in a power amplifier is how much power we get, how much we put into it, and did we distort anything, and are we working on the right frequency? Pretty straightforward. It turns out, in general, what we really do with a power amplifier is we determine how much battery we're going to use. What we do is we take the constraints of power, efficiency, linearity, and we take most of those just to an acceptable limit and put everything else into efficiency so we can do it for a longer period of time. And the trades in amplifier design and the limitations are, as you stretch the bandwidth, as you cover more bands, you give up on efficiency. So you have to give up on talk time. So the more flexible it is, the less long it will last in general. There are some new technologies coming out that try and make things better. There are fancy bias schemes and a variety of other things that are happening. They do compensate, but they add complexity and cost. So the bottom line on amplifiers is you can do an awful lot of things, but you can't do everything all at once and have it work really well yet. you can choose what you're going to do well at and what you sacrifice. The general game in power amplifiers is to cover more spectrum because we're getting more bits and pieces out there. So I thought it was useful to put up a quick spectrum map, which is the colored line in the middle of the slide. We have blue sections at low frequencies, 800 to 1,000 megahertz, 1,700 to 2,000, that are our classic bands of use. There's a variety of different bands in there listed below. The band numbers are all from the standards body 3GPP, and the blue ones are the ones active in the U.S. U.S. has a number of bands in both chunks of spectrum, and that's what you're using today when you use your cell phone, your pad, what have you. Most of the new spectrum coming out, the 700 megahertz bands and also some bands above 2,000, are where most of the LTE is being deployed. It's green space spectrum, so I colored it green. You could take the 2700 and run it up higher in frequency, but right now, most of the defined bands are below 2700. There's also some new spectrum being considered at 600 to 700. Now, what's useful to know is the bandwidth you can get efficiently out of a power amplifier is about 15%. So that's a chunk like the blue chunk there, or the green, or the upper blue chunk. And what that means is when you add this new spectrum, you're probably adding another line to power amplifiers to cover the spectrum. If you try and do one that covers everything, you're going to be running your battery down a little bit. Filters are the trickiest bit. As you'll see as I go through the presentation, most of the devices in here have a fair amount of flexibility, but filtering has very little. Filtering is all about not having two things close together interfere with each other. And the steeper you make the filtering, the higher the Q, which is the quality factor of the filter, which is proportional to the steepness of it. In a sense, it's like inertia. The more mass it has and the steeper it is, the harder it is to move. So there is kind of this dichotomy between flexibility and adjusting in filtering and steepness and having things work. There'll be some talk later today about schemes that try and address how to do tuning and filtering, but the real challenge is Q. And if you look at the technologies that are available, there's a variety of them, and they have different Q ranges. They also have somewhat different frequency ranges, but in general, most will apply in the range we're talking about. The other thing to talk about is most of the filtering in your cell phone, in order to be small, doesn't work on electronics, it works on acoustics. And this is because by working at a lower velocity, you have a shorter wavelength, and therefore the components become smaller. So the filtering is either surface acoustic wave or bulk acoustic wave, and it can be fit into very small areas. It can be done on semiconductor die, and it doesn't take any more area than a conventional power amplifier or gates or something like that. If you try and do it electrically, it ends up being much, much bigger, and it doesn't fit in the phone, essentially. So if you need good filtering small, right now the only technology we have available for that is acoustic. We do play games of adjusting with acoustic and electric together to try and get some adjustability. Then you start running into Q and limitations of things that are close together. So the bottom line is that the filtering that we use in order to be small ends up being constrained in terms of steepness and bandwidth by the technology you're using. It's also true that in the band plans, the filtering requirements vary a lot. In the filtering industry, we talk about easy bands, difficult bands, and really difficult bands. And if you boil that down, the easy bands are ones where things are far apart from each other and they have no neighbors that are problems. And any of the filtering technologies, including the adjustable technologies, work well for that. The hard ones generally are places where we cram things closer together. Most of these are FDD bands that have a small, what's called duplex gap, which means the transmit and receive frequencies are close to each other. That means you have to have the filtering be sharp enough to roll off in the gap, and that's where the challenge comes in. If you look at just the gap, it's hard to do that with the low Q filtering. If you look at channels, you can get away with the low Q filtering and things work pretty well. So there is some hope for a tunable in hard filtering if you can get down to channels rather than bands. The toughest job is the really hard ones, which generally are neighbor problems, and that's what we're seeing more and more in the industry. The issue being a lot of the best spectrum has already been used up, and what we're getting available now are pieces that can be freed, but they're things that are near other things. You now have neighbor problems, and you can either be overwhelmed by a strong signal next to you, or you can overwhelm somebody next to you. And in either case, the only way to solve that is very steep filtering. So there is a difference, and it's getting harder, and it's necessarily so if you think about how we're getting spectrum. Move from filters to switches. So switches you'd think would be straightforward, but I wanted to talk about them because they're so often ignored. Most people think, okay, it's either on or it's off, signal gets through or it doesn't. But this is an electronic device, and it's not ideal. And so the problem is that switches have what's called leakage. So it's not the signal didn't get through, it's that most of the signal went one way and a little bit of it went the other way. And the switches also have loss. So the ones that went the way you wanted them to, well, not all of it got through. So you can't arbitrarily add switches ad infinitum to the front end. You'll end up with too much loss. And you have to be careful that the isolation is high enough. And the reason I talk about this is if you look at what a cellular phone is doing, there's signals of very different power levels involved in the phone. You're broadcasting at a couple hundred milliwatts, but you're receiving signals at minus 80, minus 90. So you're talking 100 decibels, more than 100 decibels of dynamic range in these things. That's a phenomenal amount. If you look at what most switches are, the isolation is in the 20, 30, 40 dB range. So all of a sudden you can see where you might have a problem. If the leakage is a lot stronger than what you're looking for, then you have a problem in your radio. So the isolation has to be made good enough to make things work. But generally to make the isolation higher, the loss gets a lot higher, and all of a sudden you've got a problem with efficiency again. So switches end up being critical in terms of what you can practically put together, how many things you can paste in parallel, because you have these limitations of loss and leakage. Right now, the answer tends to be about 15 things, but that's been growing steadily with time, and it may get better. And there's new technologies being looked at for switches that have a hope of making that significantly better. Tunable match, I'm not going to say an awful lot here, especially since we have a tuning expert on the panel, but what is happening is because of the need for adjustability, people are looking at elements that can change their electronic characteristic as a function of applied voltage. Most of these are actually variable capacitors, and there's a whole bunch of different ways this is done. They have different advantages and different limitations. Limitations tend to be around things like tuning range or linearity or Q. And depending on the space, that may or may not work for your application. Some of them work very well. Some of them, there's applications that's hard for them to fit into right now. And basically, if you're looking at filtering, I didn't dwell on it, but I should go back to it here. If we look at the Q level of the devices in filtering right now, the L's and C's that most people think of as filters have Q's in the hundreds. It's actually very hard to find an L with a Q of more than about 50 or 60. 80 is kind of state of the art. If you look at the surface wave devices, those are Q's close to 1,000. If you look at the bulk wave devices, those hit 3,000, 4,000 in production. So there's really significant differences. If you go to what's available in the tuning, it's the LC kind of thing because it's the C with that fixed L, and you're back down into the 50 to 100 range. So that's practically what we know how to build right now. The other thing to consider in tuning is, can you adjust it while it's on? What's called hot tuning versus cold tuning. It's fairly straightforward to turn it off, go to an adjustable point that's good, turn it back on, and you're okay. But how do you get there? Can you actually vary it dynamically while it's live? And the problem is the RF signal can affect the ability to tune, and it can also have the option that the tuning goes through a bad point, something that would cause unacceptable radiation or oscillation or some other problem. So there are difficulties in tuning beyond what are the values and what are the Q. It's also how do you get there. Because remember we talked about power amplifiers, how their performance changed on their environment. If you go to the wrong impedance, then you get the wrong performance and you're not what you want to have. The last thing I wanted to talk about was antennas, and these are increasingly important. Antennas also have bandwidth, and really the issue on antennas is the lower in frequency you go, the bigger they tend to get. So 600 megahertz has a very nice sound to it from the point of view of being open new spectrum. It will have wonderful propagation, meaning it will go a long distance. It's also really going to press the antenna guys to figure out how to fit something that is that much bigger into the handset. Now, they can make them smaller by making them narrow band, but the way we try and get data through is to make the channels wide band, so there's a little bit of a dichotomy there. So adding a lot of low frequency stresses the antenna. Adding a lot of high frequency, not so much, but it probably end up being a different antenna. The other thing to think about in terms of most of the front-end components is almost all of these should be thought of in terms of percentage of bandwidth, not in terms of megahertz. So there's a tendency to take the easy way out and say, okay, I saw something that only had a guard space of 2 megahertz, so I know we can do that. You really can't. It's 2 megahertz at 800 megahertz. That you can do. But that says if you went to 1600 megahertz, you'd need 4 megahertz of guard band, and so on and so forth. So you really have to look percentage bandwidth. Antennas, high frequencies, you can fit a lot in, and it's not that bad. Low frequencies, they tend to get big, and it's hard to do. A wide range of frequencies, very tricky. Luckily, if you go back to the band plan, I'll switch back to the frequency. If you look at the blue stuff, what you'll notice is the upper stuff is twice the frequency of the low stuff. And that's good for antennas because they tend to be modal. And you can use the second harmonic and get the signal out at the higher frequency. So this 1x, 2x, 3x makes the antennas easier to build. So there are some kind of tricks in this. Okay, so that was a lightning view of some of the things going on in the front end, some of the limitations we face, some of what's going on. I know that that's probably overwhelming and more than you want to know, which is what an engineer always tells you. But hopefully the red on the bottom line gives you a reference point. In general, most of these things are adjustable, but there are limits in how far we can adjust them, and we need to pay attention to these if we're going to look for cost-effective and technology-compliant solutions that we know how to build in the immediate future. And thanks for listening to me.
Thank you. If we could have the panelists for the first panel come up. And for those of you watching remotely, we are going to try to get some of the slides posted up on the webpage because I know they're kind of hard to read on the streaming. So the first panel is going to be filter technology and its impact on band planning. We have 2 moderators for this panel. The first one is Michael Ha. He is an electronics engineer in the Office of Engineering and Technology here at the FCC. His co-moderator is Walter Johnston, who is the chief of the Electromagnetic Compatibility Division in the Office of Technology here at the FCC. And we ask that the speakers try to speak as close to the mic as you can so that the people on the live stream can hear you. Thank you.
Thank you, Cecilia. Good morning, everyone. My name is Michael Ha with the Office of Engineering and Technology here at the Commission, and welcome to the Band Plan Forum. In today's forum, we will start out with RF front-end components, which is the basic building blocks of the handsets, and then we'll move up to the manufacturers and standards, and then get some opinions from the licensees and licensed carriers and so forth. When it comes to multi-band support, RF front-end often comes as the most challenging part of a phone design due to the stringent performance requirements as well as number of components that are involved. In this panel session, we have invited industry leaders on the key RF front-end components to discuss challenges. They are faced with the complex band plans as well as the new innovations that are at the horizon. The format of today's panel is about 5 minutes of a presentation from each panelist, followed by questions and answers. The order of a panelist presentation will be similar to William Mueller's presentation. We'll start from the PA and work all the way up to the antennas. Introduce panelist.
First one's Gene. First panelist will be Gene Kachenko, who's Senior Director of Engineering, Skyworks Solutions. Gene?
Thank you. Okay, slides, please. Okay, so here's how the typical smartphone diagram is looking like today. You can see that quad-band GSM functionality is typically always there. Typical smartphone contains about 5 bands of wideband CDMA and 1 band of LTE, say band 13 or 17 for AT&T or Verizon. And it requires the front-end switch of about 12 throw functionality. So in other words, you have 12 arms on that switch handling all that switching and complexity. You can see that there is 1 amplifier, 1 filter, and 1 switch arm in this type of configuration. And if you wanted to add more bands, then in the most simple way, you would add 1 amplifier, 1 filter block, and 1 switch arm. So the diagram on the right shows the evolution of 3GPP bands, and you can see that we went from somewhere around 10 bands being supported just a couple of years ago to having over 40 different bands today, mainly driven by LTE, addition of various bands in different regions. So smartphones today have to get much more complex to be able to support this level of bands in terms of switching, filtering, and amplification. So how do we do that? The answer is higher levels of integration and multi-mode, multi-band architectures. So if you look at the diagram on the left, which I showed on the previous slide, this is what we call a discrete implementation of the architecture, where you have essentially 1 chain per every frequency that needs to be supported. This configuration is fairly flexible, so to add another band, you just add another chain and another throw of the switch. However, it takes up a lot of space and it's costly. So clearly for expanding the number of frequencies, this is not the way to go. The diagram in the middle presents the multi-mode, multi-band architecture where fewer number of PAs handle all this amplification, multiple bands. So you would have 1 high band and 1 low band amplifier. The high band would handle frequencies around 2 gigahertz, and the low band amplifier would handle frequencies around 1 gigahertz and less. And those would handle 3 or 4 bands per amplifier. Sometimes those would handle GSM signals as well. So for example, here in this diagram, the low band amplifier would handle band 5, band 8, also 20, but also you can do band 26 as well as 13 and 17. So 1 amplifier can handle up to 6 bands or even more. The same situation is in the high band as well. There is some flexibility with this type of architecture where if you wanted to add some of the ultra-high bands, you can add a chain of amplifiers and, for example, support band 7. So this architecture provides smaller size solution and is more cost-effective than the discrete architecture. However, there is the penalty of performance because 1 PA has to handle multiple bands. Finally, on the right, you can have an architecture where you integrate a lot of the same components in the same package, and you can do a lot more optimization per band. So same multi-mode, multi-band PA may handle 3, 4, or 5 bands. However, you have filters and switches in the same package, and you can optimize that solution not necessarily in the 50 ohm environment, and you can provide improved performance in terms of current consumption and others. So what are the challenges from adding extra bands? On the amplifier, this essentially means current consumption. To handle more bands, the PA has to consume more current. We talk about linear efficiency. The PA has to support linearity that is required by different standards. There is no trade-off there. You cannot trade that off. So that comes at the expense of current. With the standards evolving from HSUPA to LTE to advanced LTE, peak to average of the signals, the waveforms that our handsets are handling, are increasing, and that comes at the cost of a higher current consumption as well. So to be able to handle more bands, you have to make trades in your design so that the PA is more broadband, and there you lose about 3 to 5% in efficiency. With the architectures that I just described, the diagram on the bottom right shows that you have to have an extra band switch, and the losses in that band switch compared to discrete architecture, that also comes at the expense of additional 3 to 5% in efficiency. Also, with addition of more difficult bands, you may need more filtering. Filters mean losses. You have to add switch arms. Switch arms also mean losses. So the PAs have to deliver higher power, and therefore it comes at the expense of current consumption as well. And you have to consider interoperability between different bands. If you introduce more bands, the PA harmonics and PA intermodulation distortion may fall into different bands that you need to filter. So these are some of the difficulties. There are specific difficulties associated with carrier aggregation. This is the new standard that is being adopted and being implemented in the systems. Carrier aggregation is when you, for example, transmit on one of the bands, band 17, for example, and then you receive on two bands, for example, band 4 and 17. This is one of the common cases associated with the AT&T network. So there, as shown on the diagram on the bottom right, your transmitter can desense the receiver. Your transmitter in band 17 can desense the receiver in band 4 because the third harmonic of the band 17 transmitter falls directly in that band 4. So it's a very difficult case. That puts more strain on all of the components in your front-end chain. Amplifiers have to be more harmonically precise and not generate harmonics. Filters have to reject that extra harmonic level. The front-end diplexing and switching have to provide enough isolation for that harmonic not to get into your receiver in the band 4. There are other examples, for example, with the interaction of bands 3 and 7 with band 8, where the third harmonic is involved. And you have to be very careful with introducing these bands when considering these cases. There are quite difficult interoperability requirements, and some of the specs that need to be imposed on the front-end components need to be tightened by 10 to 15 dB, which is a significant deal. So what are some of the innovations that are coming to be able to help solve some of these problems? So integration is one of them. As I mentioned, some of the highly integrated front-end solutions can help resolve these. Tunable PAs, such as envelope tracking. The example here is the conventional DC to DC converter-based systems burn a lot more power, which is shown there as the energy in yellow, whereas the envelope tracking systems provide a dynamic supply that tracks the waveform, and the amount of consumed energy, also indicated in yellow on the chart on the bottom, is reduced quite a bit. It adds complexity. However, it provides quite significant improvements in both heat, current dissipation, and current consumption. So in addition to these envelope tracking and adaptive bias and digital predistortion techniques, there are some of the tunable components and solutions such as antennas and tuners, which we'll hear later today in the panel. And also there's a lot of ongoing fundamental device work where you need to really develop the best technologies, gallium arsenide devices for power amplifiers in particular. You have to improve and concurrently engineer these devices along with your system level performance and with your circuit and system design. Thank you.
Thank you, Gene. That was great. Next speaker is Ben Abbott. He is a corporate fellow at Triquin Semiconductor.
Okay, so we got that right?
It's not
Oh,
coming.
okay. Okay. So my talk is essentially I'm going to have just a few slides. I'm going to look at scalability, trends, and challenges for the filter components. I'm having a little trouble reading the slides, so bear with me for a minute. But I'm trying to read the. Okay, so yeah, so scalability refers to essentially how many more filters do we need to add, and that's going to be. Oh, thank you. So again, scalability means adding filters to the phone. And the bullet points there are essentially what is the impact on cost. So each filter has some particular cost. We have also size, essentially what is the footprint that it consumes in the phone. And in addition, we've heard quite a bit already about adding bands means more complexity in the phone. So I'm not going to really focus on that. I'll talk about some of the others. But on the cost, we had this is a difficult thing to parse. But in general, we can talk about simple bands and complicated bands or challenging bands. Band 5, which is the band for the U.S. cellular band, that's a fairly simple band. That's fairly low cost. Band 2 is a more challenging band, and it's typically the filters there run about 3 times as expensive. I don't have actual numbers for those. That's a little bit difficult to parse for many various reasons, but we can say something around adding a band, we can expect it to be, say, less than $2, maybe $1 or so. So just to give a range, some kind of estimate for what you can expect. So that wouldn't be such a big deal for the smartphones, but perhaps for the phones on the low end, that's a more challenging problem. The sizes are fairly small. So in this case, we're talking about, for most of the bands, we're talking about a duplexer would be something like, which would have 2 filters in it, would be something on the order of the size of 2 millimeters by 1.6 millimeters today. They can be bigger, they can be smaller. That's sort of the middle of the road. So next slide. Okay, so now trends. What we see is, of course, as new bands are being added, the big trends tend to be reducing the things that have to do with reducing cost, which is predominantly size. We want to reduce the insertion, the loss mechanisms in the filters, and increase bandwidth. There's lots of essentially technical terms. But in general, what we're talking about is making the filters perform better and cost less. These are the kind of things long term. So that's mainly for performing better. We're talking about reducing their temperature drift. These things move over temperature like many devices do. They work best at room temperature. If you go very cold, you have some problems. Very hot, you have some problems. But if you can reduce that temperature drift, they can work better. If you do that, very often you can come up with solutions that make them perhaps smaller, as an example. We also want to make them have improved steepness. So essentially, this is again a loss issue. And so we want to increase what we refer to in electrical engineering as the quality factor. What this implies in terms of trends in the industry for people who are more familiar with the products is we're going to see a larger market share for bulk acoustic wave filters and for temperature compensated surface acoustic wave filters. We don't expect many of the new bands to be easy bands. We expect them to be more like the US PCS band, which is more challenging and requires higher performance filters like bulk acoustic wave filters. There's also a trend toward, for acoustic wave filters as a parameter we very often talk about, the piezoelectric coupling factor. This determines both the loss and the bandwidth. For bandwidth, if we get higher coupling factors, that implies that we can do smaller bandwidths with a smaller device. So we expect the technology to progress to higher coupling coefficients, higher piezoelectric coupling coefficients, to allow the devices to shrink and become less expensive and take a smaller space up in the phone. And again, all of this new bands means increased integration, more duplexers, more filters, more switches, more PAs, and these sorts of things. And there's going to be challenges on the integration. So there needs to be innovations on how to reduce that complexity. And we just expect to see that to be a continuing trend. Now a slide on essentially the challenges. This is essentially a graphic. And on the graphic, we can see on the left, I have what looks like fairly simple thing. We shouldn't overlook that. This is what we very often call a brick wall filter. Very steep on the sides. It has no insertion loss, so there's no loss mechanisms. Very steep, very pretty. We see this in any electrical engineering textbook. This is typically what we see for a filter, but these actually don't exist. So this is an ideal filter that we never encounter. On the right is essentially a realistic approximation of such a thing. So you can see there are multiple curves drawn on the right. Those different colors are showing minimum and maximum sort of positions in the frequency spectrum. They're showing us essentially what happens as the temperature changes and as we manufacture one part to the next part. They're not all exactly the same. They move left or right a little bit. They even move up and down a little bit. But we have these differences between essentially the ideal filter and what we can realistically get. On the top of the filter on the right, you see I've labeled maximum insertion loss. So we actually lose energy in this, and of course this degrades battery life and other things, but we lose some energy in these filters. The loss that we lose energy also affects how steep the filter can be. So rather than having a very brick sort of shape with a vertical steepness on it, we have a finite slope on the side, and that's labeled on the far right as the transition bandwidth. We have some bandwidth we have to take. Essentially, this is a bandwidth in the spectrum that we can't use for anything. We need this as a guard band so that we can't just split things up so we just have bands straddled right next to each other. We have to have some guard bandwidth in between them. And in addition, and finally, at the far right, toward the bottom, we have what I have minimum stop band rejection. How much rejection, or we can also refer to it as isolation, we can have between the bands has some finite physical limits. And so these are where on the ideal filter it doesn't, it just goes to zero. So these are essentially the challenges we have. And so in a nutshell, the challenge is how do we move from the current realistic filter towards something that looks more and more ideal. And this is the long-term, this is a long-term trend moving in that direction. And this is my final slide, just to give an idea when we talk about the piezoelectric coupling factor, the size of the device, the quality factors of the resonators that comprise the filter, and the temperature drift. I have 4 graphics here that are demonstrating how all these can impact the filter, just for people understand conceptually what I'm talking about. In the upper left, we have the coupling factor. As we change the piezoelectric coupling factor of the filter, it allows us to get more bandwidth in the device. I don't actually have size related to that in this one. It's just showing that we can get more bandwidth. And so as the coupling factor increases, we can achieve higher bandwidths. On the upper right, I have the essentially how does the passband, the very top of the filter response, vary as we change the number of resonators. And in this particular case, I've gone from 5 resonators to 10 resonators. And there's 2 important things to recognize here. The first one is, as we increase the number of resonators, we become to look more ideal. It's becoming more square on the top. But the other thing that very important not to miss is that the insertion loss at the top is getting worse. As we do that, we're having more loss, which means shorter battery life. And this is of course something we want to avoid. So there's a real, very important trade-off in adding resonators. You add resonators, it becomes more expensive, but it becomes more ideal in terms of the shape, but you're also adding loss, which means shorter battery life. So this has to be traded off. Then on the bottom left, we have how the quality factor affects the device. This is similar, except that there isn't really a trade-off. In this case, we just want the highest quality factor possible, whatever we can do. William mentioned earlier the SAW devices tend to have quality factors under 1,000. BAW devices, we can say certainly over 2,000 are the sort of numbers. There are technologies being developed for temperature-compensated SAW devices that fall in the middle of that range. And so it's not going to be, there won't be essentially a gap. We're going to fill in the middle. The industry will fill in the middle with new technology soon enough. And this is all going to be very competitive. But in general, everybody's shooting for more coupling, higher quality factors, lower temperature drift. This is just going to be an ongoing trend. Okay, that's my last slide.
Thank you, Ben.
Okay, our next speaker will again be William Mueller, who's Strategic Marketing Manager from Avago, and he'll be talking about trends in RF front-end components.
By now I've learned to wait for my slide. Okay. What I have are a couple of individual ideas or visualizations that may help with some areas around band plan. The first has to do with filtering and Q. We talked about this earlier. I have a superimposition here of 3 different filters. In blue in the middle is a bulk wave filter, which is very steep. In black around it is a surface wave filter, which is pretty steep. And in red around that is an LC filter, which is not so steep. In green is Verizon's Band 13 spectrum. In gray, right next to it practically, is public safety. And what you will notice is only the blue curve keeps the green curve from interacting with the gray curve. You are at the very best of where we are in technology today to handle a 2 megahertz gap in 800 megahertz. And that's where we are. We weren't even this good a year ago. So we keep getting better. We keep being able to shrink the gaps. But there are differences in what the different technologies can do. And you put things too close together, then you have to use higher quality filtering, and that has a cost and technology impact. Another one. This is a colorful chart of the spectrum in PCS. The blue is the conventional PCS. The darker blue is Sprint's additional 5 megahertz, so-called G block. The orange is H block, which will be coming up for auction, or is at least proposed for that, or mandated for that, as I understand it. And the green is band 23, which is spectrum that is asking to come online. Now, what's interesting here are the two filters. The green filter says, with the best filtering we have today, we're not sure we can do it, but we can at least come close to keeping that green stuff from talking into the blue stuff. However, on the other side, we can't stop the blue stuff from listening in green's home band. The difference is the bandwidth involved. Ben talked briefly about the acoustic coupling coefficient, and that relates to the steepness you can get on the filter. On the blue filter, you need a very steep line on the left. You can't get steep on both sides, and it's much wider, so you can't get as steep on either side in the first place. And so you're stuck with this asymmetry. You can stop one from radiating in the other, but the other is actually going to be listening in the home spectrum if it gets too close. That's just the way our technologies are today. And most people don't necessarily think of this asymmetry. Another soundbite, the incredible shrinking duplexer. We've been able to about half the volume of the duplexer about every 2 years. And that's what this graphic shows. Before the bulk wave duplexer was invented in roughly 1990 for the PCS band, and that's what that green and gold second thing is. What was used were electronic duplexers made of ceramics, and that's what the big white thing is on the top. We've been slowly shrinking the size. As Ben said, today's present size is roughly 2 by 1.6 millimeters, but we actually have the ability to do it pure chip scale, which takes it down even smaller than that, and that's what can be in modules. So one of the ways around not being able to adjust filters is we can make them small enough that it's not as much size penalty of putting a lot of them in parallel. Here's another one. This is kind of geeky, but I kind of like it, being an engineer. This is overlaid spectrum plots for different modulation types. So the pink in the middle is a narrow CDMA plot, but this is the kind of thing that's used by Verizon and Sprint. The one around it in light green is a wide CDMA plot, which is what's used by AT&T, T-Mobile. And what you're paying attention to here is how this rolls off versus frequency. So notice the pink one has these shoulders on it that fall down pretty quickly. That says you don't get a lot of spectral regrowth into your neighbors, and that's kind of a good thing. The green one says, well, it kind of comes down a little more slowly and you're getting more problems, so you may need a little better filtering. Now the yellow ones behind it are LTE. They're much wider signals. LTE is a very curious system. It actually changes bandwidths in terms of the use in the phone. So you get allocated what are called resource blocks, a subset of the band, and you work on that. And your spectral density stays the same. So that when you go down to a small number of resource blocks, you have high power, and a wide number, you have low power. Well, if you look at the radiation and the spreading from that, you'll see several things. One is, on the right-hand side, there's a very high yellow line for spectral regrowth. You give somebody all the resource blocks, a very wide signal, you got a lot of noise in your neighboring bands, and it goes out quite a ways. On the left-hand side, if you have a small number, it goes down pretty quickly, but it actually is up pretty high inside the band, so you have some interference with other operators. So bottom line in all this, what kind of modulation you're doing changes a lot what you're putting out into the spectrum. And that's one of the challenges for the power amplifiers is they have to control this. They have to control the ACLR or the leakage that's going out. And the linearity requirements vary with modulation. So if you build one of these Wonder do-everything amplifiers, it now has 4 sets of linearity requirements on top of it, which it has to be able to meet simultaneously. That's pretty challenging. If we could obsolete some older systems, it would help, but we can't because different places in the world still use them. Another one is doing more with less in power amplifiers. And this is along the same lines as what Gene showed earlier. It's a multi-band, multi-mode PA. It's the block in yellow in the middle. There's a lot of complexity around it, which is a modern 10-band phone. But my emphasis here is on those black things on the right, which is what these things look like on the phone board. They're little black chunks of plastic. The one on the left is what used to be used to do this, a power amplifier for the GSM plus an individual PA for each band, like Gene was showing. What's being used on the right is what we're capable of doing today, an integrated multi-band PA and 2 satellites. Does the same job, about half the size. So that's going on in PAs as well. The last slide I have is when we're doing band plan, a really important question is what's the use case? What I mean by this is think about this in terms of you as the user. What do you want to get out of your phone? Do you want it to work for voice at home? Do you want it to work for data when you're traveling? And if it's data when you're traveling, is it okay if it only works in the hotel and the coffee shop? Gee, you can use Wi-Fi to do that. Or does it have to work everywhere in the world with high-speed data? And if it has to work everywhere in the world with high-speed data, does it have to be able to do that on everybody's network? So is one of something everywhere good enough? Or do you have to have something of everything everywhere? Or the final thing, if you could do it, what about a phone that you don't know what the spectrum plan is going to be, but it can adapt to it and go and do it? Those are all different levels of complexity. Where we are today is about you can get high-speed data anywhere on somebody's network, but you don't get a choice of networks. So that's about a 10 to 15 band phone. And with that, you can find a flavor of something everywhere. You can actually even do a good flavor of cheap data everywhere if you did a GSM phone with Wi-Fi. But you'd be limited in your data speeds and you'd be limited in where you used it. So there's different flavors, and thinking about the use case and what we're really trying to solve in a broadband plan is a useful thing.
Thank you, William. Next speaker is Art Morris. He's a Chief Technical Officer at WiSpring. He will talk to us about tunable filters.
Thank you, Michael. So, this is just to put some context. Everybody's aware of this, but maybe emphasize a couple of the points. The numbers that in the current reports are saying that there are going to be 38 combinations that are going to be needed in 3 years here around the world. We have our own roaming problems, so to speak, in the U.S. And interference problems. Whether it's also with public safety and carrier aggregation challenges. A lot of that's been addressed in earlier talks. And the incentive auctions and refarming are going to add a lot more challenges to that. Not having a clear crystal ball makes the hardware development very difficult. And so anything we can do to bring adaptability into the system is going to make everybody's lives easier as long as it provides the necessary functions. So the challenge, is the previous speakers point out, is that you have a very complex set of hardware that's being used to implement the front end of a phone. The integration is doing wonderful things. The packaging is doing wonderful things to shrink the hardware that's required. but the complexity continues to grow, and that impacts both the cost and the performance in terms of where these systems can go. It also puts a pretty good constraint on what you can really field, what's cost effective. So our vision, is to aim for the sky and actually have a fully tunable front end. The approach of making the filters, the amplifiers, and the antenna tunable can provide most of the performance that's in current handsets, and easily can provide a lot of what's necessary in the future. So the idea is to both provide what's needed and provide some future resistant capability for new capabilities coming online. For example, you could turn a band 17 phone into a band 12 phone with the software reload. So what's required? As I said, you need tunable amplification. The idea is William talked about earlier, and Gene, that if you make your amplifiers broadband, it brings challenges. It brings efficiency challenges. It brings noise challenges. Don't make the amplifiers work over any more bandwidth than they have to work. Have them be band limited and work in tunable over the range that they're needed. Have filters. They're mostly in this particular architecture to protect the receivers. As William mentioned earlier, this is a channel-based approach. It does not necessarily deal well with transmit receive right at the duplex gap spacing. But if they're paired spectrum, this approach can work quite well. And then the antennas themselves need to be tunable. There's discussion about antenna size and the bandwidth that you can get from an antenna. The smaller you make the antenna, the narrower the bandwidth. We need to pack in more antennas. If you make the bandwidth just as wide as you need, you get selectivity out of that, as well as make quite small antennas. So all of these things together will make a system that can provide very high performance. And the idea, ideally, is a system that has no switches. This is fully adjustable, no acoustics, and quite small. The efficiency of the system would be higher than in a current handset. There's just less hardware in the way. So how would this work? This is showing simulation of things that we have in development now. But a handset, in this case, it's set for band 1. If you look at the right-hand plot, this is just showing the bandpass response between free space and the actives, between an LNA, the receive chain, and from the PA out to free space. And you see a very bandpass response for both transmit and receive. And then that just tunes right across, in this case, band 1, an easy band. Losses are very low. Duplex spacing is quite wide. You go to band 2, as mentioned earlier, that's a much more difficult band with its closed duplex spacing. Losses go up, go from about a dB to 3.5 dB. But you still get the isolation, you still get the performance out of the system. And this is exact same hardware as band 1. This is just the tunable devices have changed. They're changing the programming. And then to band 4, which, of course, with its huge duplex spacing, now we're about a 0.5 dB loss. And tune that across. I then took this system was only designed for 1 through 4, and went to band 7. And even without tuning it, say we'd fielded the first system, and now somebody said do band 7. It works just fine. Up to the one limitation is the isolation is not as good broadband. So you'd have to decide whether that was worth the risk and whether you would enable this phone to operate in a network or not. But it does provide the possibility to reprogram the frequency response of the phone. So what do we need to do to make this happen? So key parts, of course, having the enabling technologies, and we, as well as other vendors, are bringing technologies to market now that are capable of doing this, having the high Qs, the high linearity, and the wide tuning ranges to make this possible. really needs to be a serious effort across the ecosystem. I mean, we're a component vendor. This really is a system change in the way that radios are implemented. So it takes people, antennas, PAs, filters, chipsets, and the system suppliers as a whole, specifiers to make something like this feasible. So it's going to take a large effort. We're going to both develop the hardware and then ensure that it's really stable, that these tunable systems are going to be reliable and stable over the lifetime of the handsets. Another key aspect, and it's not talked about a lot, is test. Even if you took a conventional phone and then you're adding 2 or 3 more bands to it, the amount of additional tests that's required before that phone can go on the market is immense. I mean, you're adding quite a bit of test time, both before it comes out as well as in type approval. This type of a system would only be able to be tested radiated, would not be conducted test. So because it's the antennas are part of the system. Now we have some of those challenges already with carrier aggregation and MIMO. So we're taking small steps in that direction now, but this is going to take a wholesale movement in that direction, both for the type approval and the production test. The next one is that the methods of type approval would change because of that. The standards right now would not support this system. So there's a lot of work to be done there. As William mentioned, the performance will be better with wider duplex spacing. As I said, if I go to a closed duplex spacing, it works, but my losses go up. So my efficiencies will be higher if I have wide duplex spacing. So the idea is going from limited bands, fixed bandwidths, and rapid obsolescence to flexible bands, bandwidth on demand, and future-proof, making things to where things are programmable. That's it. Thanks.
Thank you, Art. Yeah, the next speaker is Jeff Chamberlain from Electronics. He's a chief scientist, and he will talk to us about the antenna implications.
Thank you very much. And it is, I'll just speak briefly about what today's current antenna system looks like in a mobile device and what we have planned 1 and 3 years out in terms of increasing the bandwidth that we can service in a mobile device. It is appropriate to talk about antennas because the antenna sitting on the end of the RF chain does set the absolute frequency limit that the device will be able to transmit or receive. Just briefly, over the last 20 years in a mobile device, a cell phone, smartphone, or laptop, antennas have gone from a external stub, which tended to be a 1 or 2 frequency band standard product or semi-standard product. About 10, 12 years ago, the move was made to bring the antennas internal to the device. So today's cell phone has got multiple antennas designed into the device. They're all embedded. That provides better industrial design, and there is less breakage since you no longer have external antennas, so there are some benefits. It does tend to complicate the antenna design a bit. Also, what's complicating today's antenna design is that the industry continues to add more frequency bands required from the device as we go from 2G to 3G, now 3G to 4G. A reduced or small volume antenna does need to service a wider frequency band, so that does tend to complicate the antenna design. So I'll briefly talk about how today's passive antenna needs to and is becoming an active antenna that is tunable. Issues considered previously and today when designing an antenna system into a mobile device. As I mentioned, the frequency bands as we go from 3G to 4G are increasing, so that makes it a more complicated antenna design. Number 2, a very important factor to keep in mind as we go from 3G to 4G, 4G is a MIMO standard, so now instead of having one transmit and receive antenna, in a mobile device, we now need to have 2 antennas. And those two antennas, ideally for a 4G LTE application, should have equal efficiency, and they do need to be well isolated and decorrelated. In other words, the radiation pattern, the correlation between those patterns needs to be low. So now a 4G device, forgetting about GPS, Wi-Fi, and some other antennas we want to put into it, we need to have a two-antenna MIMO antenna system for that to enable that 4G LTE device. The antenna system that now goes into a cell phone is competing with the battery, display, and other functions inside. So we are given limited volume for the antenna system to occupy. Typically not enough volume, or not as much as we would like to provide an efficient antenna system, but nonetheless we continue to develop and innovate, whether it's a passive or active antenna system, to meet the efficiency specifications needed. We also have to worry about such issues as SAR, specific absorption rate, so that does tend to go in and complicate the antenna design a bit more in a mobile device. I thought I'd throw this one slide up to help. I think most people may not be that knowledgeable or know really what the antenna system looks like in today's smartphone. Typically in today's smartphone there are 5 antennas that we need to design and embed inside that device, a main antenna and a secondary antenna, which would provide the 2 antennas for a 4G MIMO system or a 3G main and receive diversity system. There's a GPS antenna, a Wi-Fi antenna, and now we're seeing NFC antennas being designed into the device, a near-field communication function. And as you can see, we have to sit and integrate those into a very tightly packed design. And what will happen is there will be some degradation on these antennas due to hand loading and that device getting close to a user's body. Currently, if these are passive antennas, you design the antenna, and if a user's hand goes on the device, you will detune the antenna to some level. There will be some losses due to absorption, and that's what you have to deal with. What we're seeing now, though, is some initial active antenna designs in the commercial mobile sector hitting the market, which help to alleviate or solve some of the problems like detuning of the antennas due to body loading. And also they will solve the problem of a fixed volume antenna being able to service a wider frequency range by making that a tunable antenna. There are antenna designs that are now ready for production, and some are in production now in commercial mobile devices such as cell phones that have tunable antennas that will now allow that antenna to service or cover a wider frequency range by going to the antenna and retuning it. The one antenna on the left sitting in a laptop, that's a little bit different. Instead of a tunable matching circuit, we call that a band-switched antenna. That is a second active antenna technique where we actually go out to the antenna structure and can actually retune the radiating element itself. So instead of going to the feed point and putting in a tunable matching circuit, we actually go out to the antenna structure and can actually vary the electrical length of the radiator to allow us to retune the antenna element to service a different frequency band. What we are wrapping development up on now is a beam steering technique for a cell phone. So if we can get this productized next year, you should have the capability to start choosing between multiple radiation patterns from a single antenna to provide better connectivity. That does not specifically address being able to cover a wider frequency band, but that would result in higher data rates and a higher signal-noise ratio from the antenna. And my last slide, where we want to go, and I think it's already been discussed by the other members of the panel here, is as we bring tunability into the antenna and other components in the front end, there's definitely some benefits that can be had. Number one would be instead of dealing in a 50-ohm system, we could start looking at non-50-ohm impedance matching throughout the front end. An antenna, I don't want to speak for other components in the system. Typically, an antenna is not a 50-ohm component, but we take that during the design process, impedance match the antenna so it does work well in a 50-ohm system. It'd be better if we could move down to lower impedance levels, and there could be some definite improvements that could be had from the front end by going to a non-50-ohm match. throughout the front end. Also, by bringing tunability in, it'll allow us to, as I had mentioned previously, an active antenna now, instead of being passive, it will now be able, we can dynamically tune that antenna, so in an open or closed loop fashion, there's the potential to start to keep the antenna impedance matched as a function of the environment, hand loading of the device or the device coming up to the user's head. That's all.
Thank you, Jeff. So thank you so much for the very informative presentations. I'd like to start out with this one slide, if I can bring it up. There is a strong, a compelling argument that today's data is highly asymmetrical, that there are a lot more data going down on the downlink than uplink. And we do have a little challenge of coming up with a spectrum that's paired as we have done traditionally. And the standard and technology circle been talking about this carrier aggregation, whether it's a intra-band versus interband, as is shown in this diagram. Can you give us an idea of where technology stands? Is this mature enough for the Commission to consider in our next frequency allocations, or is this another technology that's still on the development track that will take several years before we end up seeing a product? Jane, start with you.
Let me comment about carrier aggregation. I think there's this is the subject of a lot of active development in the industry at the moment. Where we have to be careful is introducing these bands that provide a lot of crosstalk between bands. And clearly we need to study a lot of cases where harmonics are thrown. The example I gave of the interaction between band 4 and band 17 generating the third harmonic and desensing the band 4 receiver, that's clearly one of the very challenging cases. There may be others. So before introducing new bands, these have to be studied very carefully. There's a lot of work on the chipset side where the chipset suppliers are developing modems to be able to support carrier aggregation. A lot of work on the front-end components, on the switches, on the filters and amplifiers. There's probably less challenge on the amplifier to be able to support carrier aggregation compared to the components sitting directly at the antenna, such as switches and filters. So that's where a lot of emphasis is. But I think if those very difficult cases of interaction are avoided, I think industry is ready to be able to support carrier aggregation.
Great, thank you. Ben?
I'm not entirely sure just what the impact on the filter would be. I'm not more of a filter device person, but my inclination would be to think that anything that sticks closer to the current situation, so where you essentially would allow, since there's not so much upload, you need some way to essentially reduce the upload bandwidth and give it to the download bandwidth. So essentially a narrower upload filter to a wider download filter would probably fit better with the current architecture. But beyond that, I'm not sure what the timing issues are with using the different bands and so on. I think it's more of a chipset problem is what I would expect.
William?
I'm assuming this relates to just downlink aggregation, not uplink aggregation, just to clarify.
Let's talk about downlink first. Since,
just for the sake of clarity there, uplink aggregation means you have multiple transmitters. Downlink means just multiple receivers. So downlink's a lot simpler, and I think the technology for downlink aggregation generally exists, that there are some things to be careful of. Gene mentioned one, which is you don't want to be harmonically related in the receive bands, because if you are, you're going to have interference issues. Another is you can't really overlap the receive bands either. Filters need some space to work together, and if you tried to have two distinct but close together bands, the two edges of the bands are going to play together poorly. They're not going to play nice. If you go to an asymmetrical so that the receive is wide and the transmit is narrow, you can do that within limits, but there are limitations on the bandwidth you can get out of filtering. It's on the order of 5%-ish right now in terms of what you can get with native good filtering. So if you go over 5% in the receive bandwidth all in one chunk, you may have a problem. So that's what I see in terms of the components. It's the technology exists, but you're adding another route for the receive, and so a little bit of complexity. and you have these conditions to be careful of in terms of spacings.
Thank you. Art?
In the near term, I think the tuning can, that's was mentioned on the antenna side can help. The antennas being narrower band, and if you're using separate antennas typically, at least in the current architectures, that helps you some with some of the interference issues. Longer term, in terms of this vision that I was painting, the ability to decouple transmit and receive and having them be able to move separately. When in that case you expanded the RX bandwidth, and it looked to me like, at least for a standard duplex, that the additional channels were further away from the transmit, so that would be even better from that perspective. But that system would you just put the receive over there. It wouldn't be any different than not having the if the bandwidths were paired. If they're true carrier aggregation, different bands, and they're still going to have to be separate chains, separate filtering lineups, and in order to be able to get the performance at both, and then aggregate at the transceivers. Yeah.
Thanks, Art. Jeff?
From the antenna perspective, we're just really concerned about the instantaneous bandwidth you're trying to service in the device. And so if we stick with the passive antenna system, what we do is, if you wind up needing to cover 5 frequency bands for a 3G device, or even more for a 3G, 4G device, from a passive antenna, we wind up having to design that passive antenna to cover a very wide instantaneous frequency band. And then in terms of carrier, band aggregation, it's not that much of a concern. We're just looking at the total bandwidth we need. Where the antenna system can come in and provide some additional improvement is, if we go to an active antenna, we can now dynamically tune that antenna. So what that means is we can restrict its bandwidth or expand its bandwidth dynamically. There's some talk today about the component values used. If we use tunable capacitors or switches, these can be very fast devices, typically 2 to 5 microsecond switching. So we can very quickly adjust the bandwidth of an active antenna, and that will allow us to expand or decrease the bandwidth as needed instantaneously, instead of always having to cover all the frequency bands, even though we're only using one band at a time.
Let me ask the same issue in a different way. The carrier aggregation is often, when we've talked about it internally, is often used to deal with I would call it the orphan band problem. We can find a band, we can't find its mate, and carrier aggregation seems to be a nice solution for that. The other technology people have talked about for that problem is TDD, and I noticed some of you had a reference model incorporating TDD. Could you talk about the pros and cons you might expect with TDD versus carrier aggregation as it might relate to the handset design? And also comment, are there any issues? The Commission, in establishing band plans, typically doesn't establish technology requirements associated with the plan. And would there be issues associated with TDD and carrier aggregation being used within the same bands? So let me start again with Gene.
Okay. So the way to think about TDD versus FDD, the FDD is more of the filter problem. That's the SAW problem. The TDD is more of the switching problem. You don't have the SAW filter there, and in most of the cases, in some cases, you still need it. So some of the solutions that we're developing today do support FDD and TDD on the front end. So it's the question of how many bands do you need in FDD and TDD. So if you are adding those at the front end, then your switch has to have this many more arms. Some of them would be to support FDD, some of them would be to support TDD bands. Again, you'd have to add more amplifier chains. You need to add more filtering. But in terms of complexities, switching complexity, with TDD, some of the filter complexity is actually going down, so that problem may go away. The question is which specific bands, how many of those bands need to be supported in the handset at the same time. So it really is down to the specific frequencies that need to be supported. The basic technology to support TDD as well as FDD and 4G is here.
Benjamin?
Actually, I liked his explanation. I don't have anything to add to that, so I'll defer to William.
Okay. So I agree that the most important thing is the specifics of the frequency. The technology to support both exists and continues to exist. There's a large and healthy TD system within LTE, and there are some mixed phones that are coming out. The Sprint network will have a mixed phone, for example, and China's going to have mixed phones, definitely. China actually likes TD stuff. And so there's a global ecosystem behind that with a rather large customer base lurking there. The filtering question on TD has to do with neighbors more than anything else. Classically, the frequencies that have been used for TD haven't had any neighbor issues, and so didn't need a good transmit filter. It only needed harmonic filtering, and that could be an LC filter. But the most recent bands, almost all of the 4G LTE bands that are TD, have neighbors, and they therefore take a bandpass filter. And so the filtering is different from, but not necessarily easier than what it is for a FDD band. There are some differences in terms of timing that have to be taken care of. Because you're doing transmit and receive, if you have multiple carriers in the same TD band, you have to synchronize everybody, and that can be a really big deal. And that's probably the hardest problem to go into that kind of scheme. In most places in the world where it's used, there's kind of one carrier has the whole band, and that solves the problem. But when you have multiple carriers, then you have a synchronization issue. Yeah, we have GPS satellites that could be an answer to that, but it's a difference in the network and a complexity in the network that needs to be dealt with.
One thing I wanted to mention on the diagram I put up of the tunable system, it kind of focused on FDD, but if you take out the filters that are used for co-site for suppression, the isolation is good enough for TDD without switches. So that's does support TDD directly in the architecture. So that would give you flexibility in terms of the front end hardware. I really don't have an opinion on TDD versus carrier aggregation. I think you want to make the best use of the spectrum you have, and in terms of the asymmetry, I understand where the TDD brings that flexibility. Although it seems like many of them have fixed ratios. It'd be nice, if they weren't fixed up-down ratios, and then that could really be dynamic. Of course, if you're doing it with frequency planning, you also have kind of fixed fractions you're working with. So I see advantages and challenges on both sides.
Really not too much to add. Once again, with a passive antenna, we just tend to design the antenna to cover all the available frequencies we need to, because effectively thinking of that antenna as that really that wide front-end filter. If we go to an active antenna, we can go ahead and start to restrict and reduce the bandwidth actually substantially. But that being said, typically for FDD system, the transmit and receive bands are close enough. We would sit and just generate one resonance to cover that entire band.
Great, thanks, Mark. So let's talk about the scalability of current architecture. Chairman mentioned that there are some congressional mandates that we have to auction several spectrum blocks in the next few years. Can you support additional 3-4 bands on your handset design for your components for the next few years? Do you see any major challenges, including cost increase?
Yeah, so scalability. So I've talked about the multi-mode, multi-band amplifiers that we're developing today to support up to 11, maybe 13 bands, depending on how you count. If the spectrum is added around 600 megahertz case, I think those same amplifiers would be able to handle those frequencies out of the same chain. The question is the performance trade-off and what is the amount of current dissipation that we're willing to pay for that. But in terms of same amplifiers supporting those bands, I don't see an issue there. The 3.5 gigahertz, that's a separate chain for the amplifier and the filter and the switch. Talking about the front-end switch, which we also sell a lot of, that's a relatively straightforward problem. Again, if we're avoiding some of the special cases with carrier aggregation where the specs need to tighten significantly, just adding a couple of arms to support extra bands is not difficult. On the filter side, I think it's just a matter of adding filters. Sometimes you can have common receive band, like in bands 1 and 4, for example, that you can reuse and have some scalable solutions. But in most of the cases, I think that means a separate filter.
Whoever like to respond.
I think from the antenna side is quite, that's really kind of a key attribute for us. As you add additional frequency bands, that puts additional stress on the antenna design. That's why active antenna techniques have been developed the last several years, because as we saw the industry transitioning from 3G to 4G, the problem becomes much more difficult to solve to drop in a 2-antenna MIMO system that covers an expanded frequency range. So it would be best, if you want to maintain good, efficient propagation, to go to an active antenna where you can go back and dynamically adjust the frequency band and the bandwidth needed. We can do a 4G antenna pair with a passive antenna system. The only issue there is you start to make compromises as you drop down to pick up the 700 megahertz spectrum, and say for a world phone application have to move up to the 2.5 gigahertz band. Now you're asking to increase the bandwidth, not only increase the bandwidth, but also pick up lower frequency bands. That's why we saw the need to really develop active antenna solutions. So it can be done, but there's going to be a complexity and a cost factor involved transitioning from a passive to an active antenna system.
Just following on that, I saw from my presentation, I think the idea is to go to something that's totally scalable. It's not going to help over the next year or two. There's a lot more work to be done on a system like that, but that's where we need to go, because that provides, the discussion about PAs and the trade-offs with efficiency, et cetera, and the bandwidth trying, you really don't want the hardware operating over any more of the frequency range than it needs to operate, the instantaneous bandwidths that are required at the time. And you will get the optimum performance out of the handset if that's the paradigm.
What I'd say is the number that you're talking about, 3 or 4 added bands, is not that hard to add to a phone, but it's going to depend on which bands they are. That's going to change things a lot, because if they're 3500, that's one kind of antenna and maybe actually pretty easy to build in. If it's 600, it's a different antenna and maybe kind of hard to build in. And it's also going to depend on how wide they are, how they overlap. Does one leak into another? Is one harmonically related to another? So it's the possible interactions of them if they're on at the same time, or if they provide paths to each other, that I'd be worried about more than the number. But I would also go back to the one slide I had. If you allocate 4 more bands, does that mean all phones need to have all of those bands? Because if a service provider only buys 2 of the 4, maybe his phone only needs 2 more bands. So that also makes it easier.
Cecilia, do we have more time for another question?
Let me ask a follow-up question. One of the problems we actually have is that, especially with smaller service providers, is that building a handset today is in some respects a custom exercise, and the smaller providers have problems in terms of getting heard, in terms of building the technology they need for the bands that they acquire. We talked about modularization and increasing flexibility in the technology. Does this hold any promise for standardizing on components that would assist in, say, the less than Verizons and the AT&Ts in building the components they need in their technology? This is also a public safety issue, too, by the way. So maybe we start with Gene again, and we'll go down.
Generally speaking, I must admit we spend more time on more higher volume and higher visibility projects. In some cases, they can be applicable to solutions in other bands, and some they do not, and we tend to spend more time where most of the volume is. For amplifiers, again, I think it's a relatively easy problem, because you can make amplifier more broadband and you can support more bands. The question is developing some of these more difficult filters. For example, I defer to the filter guys, but they may get developed after the first high volume designs are really done and nailed. So that may delay some of the technology that gets to the smaller operators. So that's, to me, that's and also just physically working on these combination of bands and these front ends. I think it just happens later because the volume is not there.
Ben?
Yeah, I wasn't sure about the question. Are you asking about if for a small player he wants an integrated module, say the same module someone like Apple would be purchasing, or are you talking about a completely different product?
Basically, the problems that the small vendors have today is that they have to custom order the filter components, build a handset specific for their band plan. And as was just said by Gene, it places them lower down on the list. I was just interested with the modularization that was being discussed. Does this offer any promise for making that a more standardized process that people could get into the game ahead of being second or third on the list?
Yes, and so I think that will happen, provided we're talking about, say, someone like Apple or Samsung orders, they have a particular architecture they favor, and if they stick to that long enough, then that becomes a standard, and those standards, those modules will then become available on the open market. But I'm still not sure that's what you're saying.
Relatively high volume, so
but those can be available in low volumes as well, right?
But it would have to be for the specific band plans of a service provider purchased. William, you have any thoughts?
Yes.
You always have thoughts.
I always have thoughts, yeah. And I'm unfortunately willing to share them. It to some degree depends on the specifics. If what you're really talking about is what happens when a relatively small portion of the marketplace ends up on unique spectrum. And that's the hard thing to figure out what to do about from an economic point of view. If we have companies out there that are working on economies of scale, we have to get a return on our design investment. And if we get a whole bunch of new spectrum coming online at the same time, we're going to Pareto that and go down the line of how many are here, how many are there, et cetera. Now, what that often does is leave the opportunity for new technology entrants to address the unaddressed pieces. But that doesn't necessarily mean you have a good solution online for the smaller players. Sometimes it depends on the specifics of the band. Now, we have the situation in the U.S. right now with Band 12 and Band 17 where this is true. Band 17 is getting components, Band 12 is not. But I think the reason for that is the band plan and not the volumes. Everybody would use Band 12 if it were easy enough to build. Nobody knows how to build Band 12 because there's no guard band to interfering services. Since nobody can build it and we can build Band 17, we build Band 17. We know what that one's supposed to do. Public safety is a different issue. That one, we kind of know what to do, and it's not that hard to do, but there really aren't that many of them, and it's not rolling out yet. So that's a timing and volume issue. The easiest way to get that going is to have some major player decide they're going to include that functionality in their handset, or something to get the volumes up. But if you do have somebody on specific different frequency, there's an investment that the component makers have to make the components. And I don't want to talk numbers. I don't think that's appropriate in this forum. But some of the bands that have been purchased have ended up in situations where the use pool is smaller than the investment given other opportunities out there. So it does create awkwardness. Now, there is a possible way around that, which is back to the service providers. In a different forum, we were talking about this in a symposium I was at before. If you look at band plans around the world and you look at a way to have one of something everywhere, you can come up with 4 or 5 flavors of that end up including all the carriers, and that includes the smaller guys. And so if you can get the service providers to kind of agree that, okay, I'm a member of list A of components I want in all my handsets, suddenly by aggregating carriers rather than frequency bands, you now build the economies of scale to have a module to support that, and it works. But that takes a fair amount of work in the industry that doesn't exist right now to create that ecosystem.
Yeah, I think this is one of the best opportunities for the tunable system. We built something for 17. It would work for 12. It would, you could flip TXRX and work for 13. It'll go to public safety. It'll go to sort of support whatever's necessary there. The problem is it's not available today, so it's not an immediate solution. But in this case where the duplex distances are all relatively similar, it's just a matter of software that would be the differences between them.
Yeah, from the antenna perspective, I mean, the antennas in today's mobile device are custom designs anyway, so it's really more of a business decision of taking the design time and the tooling costs and amortizing over a smaller production run. If your project is directed toward a carrier that's going to have a limited production. As we move forward to an active antenna, there is a potential, and it's a little bit early to tell, but there's a potential to design a active antenna, which will be a passive radiating element, and then some active components that are coupled to the antenna to dynamically tune the antenna. And there's a potential to take that tooled antenna element structure and move it from one device to another without needing to customize it and just change the lookup table or control signals that are going to the active component. So actually moving from a passive to an active antenna, there is a potential to start having less customization from one device to the next and start achieving those economies of scale.
Thank you. So let us take a couple of questions from the audience before in the panel. First one, it says, given interrupt challenges, should FCC design band plans allowing for slightly less performance, such as a Q factor, and hence more tunability/interoperability? So it sounds like you relax some requirements on one side and increase on the interoperability. Yes. Okay, it helps your business for sure.
It would make phones cheaper, but it would make spectrum harder to find. How do you do that? So I don't know if that's practical. I mean, sure, it's nirvana. It'd be a nice thing from the point of view of making the components easier. And where we can, that's a good idea. But we also have legacy systems out there. Do we take down all the legacy ones that are not so easy? I don't know that solves the problem for us since we have those to deal with.
Maybe an additional comment. One of the key things is the tunable system kind of changes the mindset from what are you the channels you're operating to protecting against the rest of the world, and that's where your challenges are. And so the ability to take these systems and not optimize them for the worst case scenario, but have them cognitive effectively and compensate for what the real interferers are at the time, changes the requirements quite a bit. So I think that's a key part to this is getting away from worst case planning, because that's what we have to do with fixed components at this point.
Great, thank you. Cecilia, one more, or are we? Okay. Another question from the audience says, as Mr. Mueller pointed out in his remarks, there are a few easy bands being brought to market. Okay.
This was a question about TDD and carrier aggregation. I think we've gone over that.
TDD versus FDD.
Yeah.
Okay. So maybe we'll take this one. For Gene, for TDD, a handset has only a fraction on the time to transmit, reducing the energy per bit unless the peak power is increased. Is the peak transmit power the same for TDD and FDD signals?
It's driven by the losses of the filter, of the SAW filter versus the switch. That's really the simple answer. In terms of the efficiency of the network, I think there is a debate online in terms of whether TDD is more efficient or FDD. I'm not a systems guy. I'm not going to venture into that territory. I don't think there is a clear winner. There's a school of thought that TDD provides better spectral efficiency than FDD. I think it's to be decided. But in terms of the power that's the power amplifiers are designed to, and the transmitted power, it really depends on the losses in your SAW filter that is required for FDD or the one that's required for TDD and the switching.
Yeah, in an unfiltered case, the peak to average is set by the modulation type, and since the modulation for TD-LTE and FD-LTE is pretty much the same, no difference there. But I mean, there are other TD systems. GSM is it's a TD-FD system, so it could be treated either way. So it's the modulation type that sets that, not the power amplifier. And the power amplifier has to align with the modulation type. And then whether the filtering is more or less lost depends on which band it is. And if you have some of the Asian TD bands or European bands get very close to Wi-Fi, and they require fairly lossy filters in order to keep them out of Wi-Fi. In the U.S., we don't have too many of those.
Thank you. That's it? Yeah, I think we're already 25 minutes behind the schedule. So.
Okay. I'd like to thank the panelists. It's been a very interesting and informative discussion, and I greatly appreciate your coming.
Thank you.
So we're going to take an hour break, hour and 5 minutes, if everybody can come back at 1. We will have people in the back of the room escorting those here. Could we have all the speakers come up front, though, for just a minute? And if you want to go down to the lunchroom, you need to be escorted down to the lunchroom and back. So we'll have a couple of FCC staff standing in the hallway in the back to take you down. And then shortly before 1, we'll come down to bring you back to the room. And for those online, we know that we're having a little bit of technical issues, so we are trying to get copies of the slides posted. And if you could try after the break to reboot your computers, we are working on the technical issues. And those here in the room, we're going to have copies of the presentations for the afternoon printed out so that you'll be able to follow along easier. Thank you. While Chris is speaking, we ask that the speakers for panel 2 could come up into this front row here so we can have a quicker transition. I know we had some technical difficulties this morning, but we think we've got everything fixed and up and running okay. Please, if you're watching remotely, if you're having any issues, send an email to livequestions@fcc.gov, or if you have any questions for the panelists. Again, here we have Lisa's in the back there. If you want to raise your hand, Lisa. She has the note cards and pens, and if you have questions, just raise your hand, and she or I will come around and collect the questions. So the next presentation is going to be a presentation from the FCC, and it's going to be given by Chris Helzer, who is an electronics engineer in the Wireless Bureau here at the FCC.
Hi, thank you very much for coming. As Cecilia said, my name is Chris Helzer. I'm an engineer here at the FCC in the Wireless Telecommunications Bureau. And I'm going to give a brief presentation on some of the ideas the FCC has had recently about band plans and how band plans might be different in the future than they are today. And I'm not going to take any questions during the presentation. A lot of the same topics are covered in panels 2 or 3, so if you think of a question that might fit into one of those panels. And I think Cecilia may have forgot to mention, but for those of you who are having trouble seeing the screens, we do have printouts of all the slide decks are available over at the table here. So if you can't see my slides on the screen, feel free to go get a printed copy. Not that there's that much detail in them anyway. And so if I could have the slides up on the screen. So traditionally, when we have a kind of traditional way we do band plans, which is there's a large amount of spectrum is cleared from whatever previous existing service, and we take it and we split it up one of 2 ways. Either we assume it's going to be an FDD band, and we split it in half, make half of it uplink and half of it downlink, or we assume it's going to be a TDD band, and then it's just large band, one large band. In both cases, there may be a need for a guard band at the edge, because it depends on what services may be adjacent to the spectrum you just cleared, whether you can actually use all the spectrum without impacting adjacent services or being impacted by adjacent services. And in the case, that's true for both FDD and TDD. In the case of an FDD band, we traditionally have done symmetrical, equal-sized blocks, evenly spaced, constant duplex spacing, and you need to have a duplex gap in the middle which separates the uplink from the downlink and makes it functional. Obviously, in that case, you're obviously pushing towards a smaller duplex gap because you're generally trying to allocate more spectrum, although there are things you can do in the duplex gap, so that's not always the case. TDD is very similar. TDD, obviously, the uplink and the downlink occur on the same frequencies, so you don't need to allocate two chunks. But you also have the problem that if operators don't synchronize, you may need guard bands between every operator or between every block. We don't traditionally allocate those explicitly, but they may be needed. And as a matter of fact, it's a general topic as to whether guard bands should be allocated explicitly or left to, if the spectrum should be allocated, it should be left to the spectrum holders whether to try to make the best use of it or not. I'm not going to talk about that much today. That's more of a policy issue than a technical issue. So as we look at new spectrum becoming available, there's 4 or 5 things that come up that are in this deck. One is having what we call a very large duplex gap. Instead of the days when we would find 100 or 200 contiguous megahertz are probably behind us now. And so the idea that we get this big chunk of spectrum that we can afford to split into uplink, downlink, and duplex gap is probably not going to be happening so much. We're much more likely to find 30 megahertz here, 10 megahertz here, 50 megahertz here. So one of the questions that comes up is how far can we separate uplink and downlink? You know, in our kind of traditional bands like cellular and PCS, they're quite close to each other. And then we have a band like AWS where they're quite a bit farther apart. It's 1700 megahertz and 2100 megahertz. I don't know what that is on a percentage basis, but they're like 15 or 20% apart from each other. So it's fairly significant. And as you heard on the previous panel, people are now talking in the standards about things like carrier aggregation, where they're using an uplink carrier maybe at 700 and a downlink carrier at 700, but a second downlink carrier at AWS or 1700 or 2100, some high frequency. And so that raises the question from our mind of, can we just take any 2 chunks we find and make them a pair, or what are the limitations on what we can do? So that's one of the issues for us, is the large duplex gap. Does it make sense to find something here at 1.7 or 2.1 or 2.5 and pair it with something over here at 1.8 or 700 or 800 or 600? That's the first issue. Obviously, there's antenna challenges there. I'm sure we hear about that, but there are maybe other challenges as well. Another issue, which we'll talk more about in panel 2, is asymmetric allocations. A lot of the spectrum these days that we're looking to allocate is for mobile broadband. It's spectrum we want to allocate as part of the National Broadband Plan. And the broadband traffic right now and the forecasts we see from companies like Cisco have a lot more downlink than uplink traffic. And the standards to some extent take that into account, and they're more spectrally efficient on the downlink and more coverage optimized on the uplink, but not nearly to the degree of some of the imbalances we see. So this raises the question as to whether we should, if we're doing FDD, should it be done asymmetrically? And you can envision 2 ways you could do that. It could be kind of in a fixed asymmetry where we have fixed blocks with fixed relationships, but maybe the uplink blocks are smaller, half the size or a third of the size of the downlink blocks. Or it could be something different where we have 2 bands and they're both split into equal size blocks. There's just more blocks in the downlink band than the uplink band. And then this would be a little more market driven. It would be up to people to attempt to acquire 2 downlink blocks for 1 uplink block or 3 downlink blocks for 1 uplink block. And it's possible that people would even acquire blocks as downlink expansion, blocks that they just use for downlink with some other uplink spectrum they already own. There's been a little talk about downlink expansion. Some companies have been considering that for a 700 block, and I think Orange in France briefly mentioned they might be considering some spectrum for downlink expansion as well. Another idea, which is a little more complicated, a little harder to explain, but as we look at these different pieces of spectrum coming online, the availability is not necessarily going to be nationwide. A lot of these bands that we see have a lot of exclusion zones, a lot of services that can't be cleared immediately or maybe can't be cleared for a long time. And that presents a difficulty because obviously you prefer to have a single nationwide band plan. But one of the thoughts that's occurred to us is that there's a big difference in the economics of the devices and the base stations, and there's an asymmetry in that situation that we can maybe reflect. So if you think about a device, the device has to travel across the whole country, if not the whole globe, and it really needs to have just one filter or at least as few filters as possible. You really want to minimize, I mean, you heard in panel 1 about all the duplexers and switches and antennas and so forth we need for each band, and you don't want to make that problem worse. So it seems like it's really critical in the downlink band to clear it nationwide, to have something that's spectrally clear nationwide for downlink, because that allows you to have a uniform device receive filter across the country. On the other hand, it's not clear it's so critical for the uplink band. Here you're looking at the base station receive filter, and a given base station only operates in one region. They don't move, except for CALs in a few special cases, but generally they don't move, so they don't need to support, they would only need to support the regional band plan. The device obviously moves, but generally devices can meet our transmit requirements without a transmit filter. You heard in panel 1 that, for example, a GSM device or a TDD device might not have a transmit band filter at all because it can meet 43 plus 10 log P just based out of the PA. And so and in addition, the device isn't going to be assigned spectrum by the base station that the space station can't actually receive on, so you don't have to worry about a device transmitting on an unassigned frequency. So this opens the question of, if we are finding uplink here and downlink here, if we find an uplink band that has maybe some serious exclusion zones that we require to actually be 3 separate band plans in 3 separate regions, but pair that with a downlink band that's uniform, that might be a way to put some of the spectrum into use that otherwise could not be put into use without overly burdening the devices. So that's another one of the strange ideas we have here. We're also thinking a lot about block sizes. In the past, we've often based the size of the blocks on what we were clearing and what was there before. Like in 700 megahertz, we're clearing 6 megahertz channels, and we mainly just cleared a channel and allocated it, so we allocated a lot of 6 megahertz blocks. But we see the standards are moving very much towards multiples of 5. HSPA and WCDMA are multiples of 5. LTE does support some other smaller bandwidths, which are 1.4 and 3, but it's mainly 5, 10, 15, and 20. So it seems we should probably be allocating blocks of multiple 5, at least for bands we expect to be used for mobile broadband. But that does raise the question of, well, which one? Should it be 20? Should it be 15? And I think one of the things we're thinking is we should allocate blocks of 5 and let people, if they want to do a 10 megahertz carrier, get 2 blocks, or if they want to do a 15 megahertz carrier, get 3 blocks. Obviously, there's some issues. If that was an auction situation, we might have to guarantee that you'd get contiguous blocks, otherwise that might not be as useful. But so that's the kind of thing we've been thinking about as well, is there a kind of uniform block size we should be using in any band intended for mobile broadband? And the last issue, which is kind of talked about a lot on panel 1, and it's also talked a lot about in there's a working group in the Technological Advisory Council called the Multiband Group that works on this, which is there's a band proliferation problem. You can only squeeze so many bands in a device, at least until we get fully tunable front ends, which we heard some about in the first panel. And so there's a lot of bands out there. This slide will probably be extremely hard to read from the screen, but the orange blocks show all the 3GPP bands that are already allocated in North America. So you can see there's a whole cluster of stuff down in 700 and 800, which is bands 12, 13, 17, and I forgot the other one, 14. And then we have the cellular band and the extended cellular band, which includes some of the SMR spectrum. We have the L band and the S band MSS allocations. We have PCS, we have AWS, and we have band 41, which is up in the BRS EBS spectrum. We have all those bands already, and then the red blocks, which are pretty hard to see, show things that were required to auction in the next 2 or 3 years. There's an undefined chunk of television through incentive auctions. We don't know what the participation will be. We don't have final rules, so we can't tell you how much megahertz or which frequencies, but that will probably be a new band. There's a requirement to auction 15 megahertz in 1695 to 1710, so that's a band. There's requirements to auction the H block, which is adjacent to PCS. Those are very small red blocks, if you can see them next to PCS. There's a requirement to auction a lot of the spectrum between 2155 and 2180. There's not a pairing for that, but if we're right that downlink expansion is a good idea, maybe that's how you auction that. And then there's other bands as well. There's bands that there have been a lot of discussion of federal sharing of those bands. Those are marked in purple. You see 1755 to 1780, and you see it's, I think, 3550 to 3650 at the very top. And there's also a few other bands that are currently allocated that could maybe become mobile broadband bands, like the WCS band or other bands. So lots of bands, lots of spectrum that we have to come up with band plans for, but also an issue about band proliferation and how many bands we can support, and to what extent we need to prioritize bands that can be seen as extensions of existing bands, or at least are harmonized with other global allocations, so we're not doing too much to contribute to the number of bands. So that's actually all the slides I have, I believe. Yes? And I've used up most of my 15 minutes trying to run through those slides, so I think we'll just proceed to panel 2. Thank you very much.
Thank you, Chris. So if we could have the speakers for panel 2 come up. So the next panel is going to be on LTE trends and their implications on band planning. We have 2 moderators for this panel. The first is Chris Helzer, who just gave the fabulous presentation. And then we have Brian Daly, who is the director in the Office of CTO for Strategic Standards at AT&T. So he's going to be co-moderating with Chris.
Okay, thank you, Cecilia. Thank you everybody for coming here, for listening to my thrilling presentation, and for coming to watch our panel. And thanks to all the FCC staff who are helping run the event today and who helped get the event set up and organized in the first place. And thank you to Brian for agreeing to co-moderate, which is very kind. I'm going to go ahead and introduce the panelists first. We have Al Jetty from Nokia Siemens Networks, where he's the head of North American and global standards, I believe. Well, North American standards, sorry. Steve Wilkes from Alcatel-Lucent, who's a distinguished member of technical staff there and has been working on RF network planning with carriers and a variety of radio issues for a long time. Peter Gall at Qualcomm, who works on standardization and prototyping of LTE technologies. Erica Theodore from Ericsson. She represents Ericsson in the LTE standards in the RAN 4 group, which works on adding new bands, actually, so very appropriate here, as well as specifying performance for those bands. And Bill Alberth, who's the VP and CTO of mobile devices at Motorola Mobility. So thank you all for coming. And I think we're gonna start asking each of you a question that you knew about ahead of time, so you have some slides. And I think Brian Daly will ask the first question.
Thanks, and we'll start with Al. We've heard in the previous panel, that there are predictions that there are going to be significantly more downlink usage than uplink usage in the future. And we see developments of the standards, such as carrier aggregation, to support that seem to allow symmetric FDD. Can you tell us about the need for and support of asymmetric FDD in the standards?
Sure. Thank you very much, Brian. And Chris, thank you. Whoops.
What? You have a clicker there.
Okay.
So you know, once the slides come up. There you go.
Okay. Thank you very much, Chris, for having me here. And Brian, really an excellent question. When we take a look today at the data in balance, we're seeing, on this slide, on the left side, this is data that NSN took from one of our systems, and this is a commercial system in Europe. We were looking at LTE data. And you can see over time, this is like a 2-month interval, that the downlink was about 13 times greater than the uplink. So clearly this goes to what you said, Brian, about the imbalance. We also have on the right a chart here, and this shows from some data from Cisco, and I think it was a lot, and they were showing between 6 and 10x in evolving to maybe as much as 12x difference. So I think everyone in the industry is not only seeing the difference and predicting the difference, and it's a fact, okay. And I think there's another panelist who has a slide that even shows a greater imbalance, okay. The people are watching a lot more video on their devices, and this is causing a lot of downlink, traffic, whether you're watching YouTube or whatever. Now, I do want to footnote this, is there are some special events where the uplink traffic is equal or may even be greater than the downlink. For example, at a Super Bowl or some major rock concert, you may have people shooting pictures or video and uploading it for their friends to see. But let's just consider that a special event. But in general, we're finding there's a lot more need downlink than uplink. Okay? So one thing, when you look at the downlink, there's one good thing for it, is it's usually 2 to 3x more efficient than the uplink. If you look at a base station, you've got a larger power amplifier, you're going to see it 2 to 3 times more efficient, or being able to carry more data than the uplink. So that kind of helps out, the problem a bit. Okay. And the allocation of resource blocks, or this is, the quantum for the base station allocating, resources to users. This is done in resource blocks. And the base station can allocate, so many resource blocks for downlink and a different number for uplink. So if there is a lot more downlink traffic, the base station can allocate more resource blocks for the downlink than for the uplink. But today, as you say, you've got paired spectrum. So if you're allocating a lot more resource blocks for the downlink and less for the uplink, you have some uplink resource blocks that just go unused. Okay. Now, one of the topics that's been talked about a bit here is carrier aggregation. And carrier aggregation is where you're going to aggregate 2 carriers on the downlink and maybe 1 carrier on the uplink. Okay, carrier aggregation is a future topic for 3GPP on the uplink. Today they're focused on the downlink. And there's a lot of problems with supporting carrier aggregation even on the downlink, because if today you've got paired spectrum and you've got 2 carriers, or 2 channels, let's say, downlink and uplink. So if you're going to carrier aggregate on the downlink, you still have that other paired spectrum on the uplink. Okay, now you could get by and say, okay, we're going to have this uplink channel we're just not going to use, or you could even have it as some imaginary uplink channel. For example, if it was the D block or some TV spectrum that really was only downlink, the standard today says it's still going to be paired, but you don't need to use the uplink pair. Okay, so as you're doing carrier aggregation, this does allow you to increase your peak downlink throughput and slightly increase the overall average throughput. So this will help out the problem a bit here going forward. Okay. Let's see. So getting back to your original question, Brian, I'm going to circle back. I think that they should look at, the FCC should look at and study, possibly having, 2 to 3x as much downlink spectrum as uplink spectrum, and I think that would help, operators with their needs today. Okay.
All right, thanks, Al. That's very helpful. As a kind of follow-up question for Steve, obviously the 3GPP standards support TDD as well as FDD, and so can you kind of compare and contrast how the asymmetry could be supported in either case, and if you also see the same need for the asymmetry that Al just talked about?
Yeah, it's very good, Chris. Yes, I'll bring up our view graphs here, but just point out that indeed the 3GPP LTE standard supports TDD, time division duplex, like a ping-ponging approach to the sharing of the uplink and the downlink resources versus FDD, which has a separate lane for downlink and uplink. Do I need to do something to bring up my view graphs? All right. There's a bridge near here in Bethesda, I think, called the Union Bridge, that was built in Civil War, that was made from an aqueduct to a road, but it's a single-lane road. And TDD is a little bit like that single-lane road. You can only have traffic go one direction or the other direction at one time. but these don't seem to be my view graphs. If there's some way to pull up the Wilkes, Alcatel-Lucent, ALU view graphs. And I'll just try and stall a little bit more by pointing out that as Al pointed out, we're seeing a great asymmetry in the demands for the uplink and the downlink traffic. Thank you very much. As I show here, a year's worth of traffic on one of the major network operators showing 17 to 23 or even 30 times as much downlink traffic as uplink. I don't know how this compares to the earlier comments, but this was for physical layer 1 traffic only, so it may have included, well, it did include a HARC retransmission request. So this is looking at the spectral demands of the uplink versus the downlink, and not just the traffic that does not include at the layer 3 type traffic. So we see that there's this great increased load in the downlink. In the a few years ago, with voice traffic, it was 1-to-1 ratio, and about 5 years ago, I looked at some of the traffic, and it was looking like it was 4 to 6-to-1 downlink heavy. But with the smartphones, and since 2007 or so, it's overwhelmingly downlink. There are these exceptions, both Super Bowl type venues, as well as other operators may be different. And of course, just like in the stock market, past performance is no guarantee of future results. Could be another application will come out next month that'll change things entirely, or you'll have wireless video cameras watching our houses all the time, and things like this wireless surveillance may change things. But this is a big boat, and it's going to be hard to turn around. Let me address your question, though, about TDD's capability of addressing this. And with LTE, there are 9 formats for handling TDD traffic that change the trade-offs between uplink and downlink resources. From one in particular supports configuration 5, and the table shown here is supporting 8 downlink time slots for the 1 uplink time slot. So this could support an 8-to-1 ratio of traffic. None do better than 8-to-1, and like I say, we're seeing more like 20 to 30 times as much downlink traffic. There are other limitations to the TDD air interface. As we give less time to uplink, that means that the energy per bit is reduced. So we either have to reduce the number of bits, or we have to increase the peak power, which is a problem for the power amplifiers in the handset. So at cell edge, TDD is disadvantaged, so that we have to either shrink the cell size or suffer the consequences. So TDD is highly constrained in being able to fully take advantage of the demand asymmetry. So there is carrier aggregation, as Al pointed out, which the LTE standard supports since Release 10, which we expect to see commercialized next year. And this allows us to support both different size and numbers of carriers for interband as well as intraband component carriers. Downlink-only carriers are also being supported in the Release 10, as we'll see in, say, the 700 megahertz D&E blocks, which are downlink only. And so that downlink traffic is controlled by an uplink that has to be in a different block of spectrum. This provides us these new opportunities for unleashing the capability of the stranded bands, such as, say, the AWS-3 band, which has a downlink component that's somewhat available now, but no uplink band that's been identified. But even in things like the WCS band, or even the A block of the lower 700 megahertz, where the uplink is constrained by interference to TV channels, TV channel 51, if even today, one could have downlink only capability of the A block in those markets that have a TV channel station 51 present. So there are these abilities to not only improve the ability to address the asymmetry of traffic, but also go beyond that and unleash spectrum that's already somewhat orphaned or stranded. It is not a panacea, however. There are some severe limitations and constraints on what kind of carrier aggregation one can have. There was a mention earlier today about the band 4 and 17 harmonic relations that are a problem. And there's also, it requires multiple receivers being active at the same time in the same handset. A tuned front end can't be tuned to vastly different bands at the same time, for example. And the stresses on the signaling channel, the more constrained uplink channel, would have to be handling the uplink from two different blocks of spectrum. So it's no panacea, but it's a good opportunity for us all. Thank you.
Just a reminder before we move to the next question, speakers, if you'll speak into the microphones the entire time so those on the broadcast can hear. Let's move to Peter. Another critical aspect of band planning is the size of the allocations. Can you tell us a bit about the block sizes supported by the standards and how that might change in the future?
Yes. Thank you. Yes. So in the slides, I'm trying to address exactly this question. Chris mentioned at the beginning that there might be new ways to allocate blocks, but every block allocation has to map somehow in the bandwidth that is supported by the LTE standard. So I was trying to address both what is supported today and what could be supported in the future. Today, we have 6 bandwidth cases. Those are listed here. And for each, there is also an occupied bandwidth, which is, as you can see, is less than the actual bandwidth. That is to give some guard band, as usual. It is 10% most of the time, or for most cases except 1.4. So 1.4, there is a larger guard band. The reason for this is that the waveform itself, even with perfect linear components, has some emissions that requires about 150 kilohertz guard band on each side, and we cannot really go down below that. And also another aspect is that although these are defined, they are not defined for all bands. So every band has a subset of these. I mentioned that many bands don't support all. Maybe I should have said actually that the majority of the bands, there are only a few that supports all, and most of them don't. So there is a subset only defined. So far, what we are seeing is mostly 5 and 10 megahertz cases. And by the way, 5 and 10 megahertz bandwidth is defined for all bands. The remainder are not. And the 1.4 and 3 megahertz cases are fairly rare. There is also carrier aggregation, as was mentioned before. One aspect of this is that each component carrier that is aggregated has to be backward compatible. That's the current design. And because of that, as building blocks, the aggregation has to work with these bandwidths that are defined today. Okay. Thank you. So what could be done next? So what kind of new block sizes would be possible? It was brought up, for example, before that there are 6 megahertz allocations, and it would be nice to be able to address those. Unfortunately, it's very difficult to define anything new. And although the physical layer standard already supports not only the 6 defined cases, but 105 possibilities with RB granularity. 1 RB is 180 kilohertz, so we could go from 6 to 105. Any possible number between is actually supported in a physical layer. It just there are no performance requirements for defined for these, so nobody knows how to build these devices. It's not possible to build components for them today, and they are not deployed. If there is a very strong motivation to actually deploy any of these, it would be possible, but that has to overcome the significant hurdle of defining all these for performance requirements. Next, moving on to asymmetry block allocation that was mentioned before. That would definitely be possible, and similarly, as mentioned before, it's already supported both in the physical layer and the signaling. So the UE, even today in theory, could be given a different uplink and downlink allocation. And as was mentioned before, it would be an interesting aspect to have a band that is has more downlink or uplink, but going beyond that, maybe it could be even more operator specific. So there is an example given here. I would skip the details, but the point is that different operators may actually predict different mix of applications requiring different uplink-downlink ratio. So if we could provide them the tool to actually get bandwidth closer to what they predict, it would be a useful feature. And again, it would be possible. There are some caveats that are listed at the bottom of the slides. The first two are probably good practices that should be exercised when allocating. It should be contiguous. There should be care taken for the minimum duplex separation. For example, one operator should not be getting downlink and uplink at the closer edge versus some other operator at the outer edge and things like that. But going to the last 2 points, even though if somebody follows these principles, today there is no performance requirement defined. So that is the most significant hurdle right now. And especially for the variable duplex separation, it seems kind of easy to do, but it really creates some complications in the implementation, but I will skip those details here as well. So finally, as a conclusion, the best is probably, the best prediction is that multiples of 5 megahertz is the easier and the most likely allocation in the future. Anything else would be quite difficult to do. Having asymmetric allocations is definitely a possibility and is expected to happen. But we have to be mindful about the performance requirements and how long it's going to take to develop those. Okay, thank you very much.
Thank you very much, Peter. Yeah, you skipped it, but that's okay. We'll let you make those points later. Erica, as we do try to bring more spectrum online, obviously there's these issues with the guard bands as well, particularly if we allocate an uplink band near a downlink band or vice versa. So could you kind of talk to us about what the constraints and the standards are on uplink being next to downlink, as well as what level of support there is for unsynchronized TDD operations? Thank you.
Thanks for the question. First, I would like to thank the FCC the opportunity to be part of this workshop. And I'm here today to talk about frequency planning and in particular about uplink to downlink separation. So the increase of data traffic in the network leads us to use every available hertz. And this is often at the expense of duplex gap and guard band, which were previously used to ensure performance. For example, if we look at the figure on the right side, we can see a pair band on which the width of the passband has been maximized, while it has been reduced the duplex gap, and this is the separation between own uplink and downlink. New identified spectrum is sometimes close to existing spectrum, which reduces the uplink to downlink separation between different bands. And when talking about distance between uplink and downlink between different bands, we can think about 2 FDD bands, or 2 TDD bands, or 1 FDD and 1 TDD band, as represented from figure 2 on the slide. So this small uplink to downlink separation has no precedent in existing networks with large number of users. So what are the consequences in terms of performance? And here we have a quite busy slide. But to study the consequences of uplink to downlink close separation, we look into coexistence between systems, and this is in terms of base station or UE emissions from the aggressor, and base station or UE blocking rejection from the victim. So if we think a new allocated band which uplink or downlink is nearby a legacy band, we have to think that there will be that it will affect performance on the already deployed band. Since a new base station or UE interference will appear close to the band edge, and new base station RU emission requirements will be required for the legacy band. Now, if we look into the UE coexistence point of view, a large power backoff is needed to maintain the unwanted emissions, which translates into coverage and throughput reduction when the uplink to downlink separation is closed. Or, if considerable power backoff is not allowed, the UE unwanted emissions will be relaxed, and this will increase the UE to UE interference. And also, additional blocking rejection may be needed from the victim UE. Looking into the base station side, non-standard solutions may be needed to fulfill the base station emissions for coexistence, and also additional blockers resilience may be required for the victim when the uplink to downlink separation is reduced. If we think of collocation, actually collocation between base stations may not be possible if we reduce the uplink to downlink separation too much. Looking into today's 3GPP default requirements, we can have an idea on how much uplink to downlink separation we are considering when we think about the requirements specified by the standard. So if we look at the base station coexistence, the base station emissions for coexistence and collocation are defined 10 MHz from the downlink operating band edge, and the out-of-band blocking is defined in general 20 MHz from the uplink operating band edge. We also have additional requirements which apply 10 MHz from the uplink operating band edge for collocation. Now, from the UE coexistence point of view, the UE emissions are defined at a large separations from the channel band edge, and the out-of-band blocking is defined 15 MHz from the downlink operating band edge. And also, in addition, for TDD, the requirements are specified for synchronized adjacent systems. Now, if we think about uplink to downlink separations, which are smaller than these numbers, exceptions may be required with possible risk to performance. And this concludes the presentation. Thank you.
Thank you, Erica. Bill, another aspect of band plans, at least for FDD, is the size of the duplex gap and the arrangement of the duplex spacing. What can you tell us about how this influences the standards?
Thanks, Brian. Well, while we're waiting, Mark Twain used to say, buy land, they don't build it anymore. And if you were here today, you'd probably say, buy spectrum, they don't make that anymore. We would all love to be able to take the spectrum and wipe everybody off of it and then be able to allocate it like we want, make it perfect so that it fit with existing technology, and that's just not the case. We've got legacy deployments of billions of dollars, and as new spectrum blocks free up, we're going to have to find the best ways to use them. So a couple rules of thumb for duplex filters. Really, when we talk about duplex gaps and duplexing and the space between the spectrum, it's a question of how can we build filters to accommodate those frequencies. We would like to, where possible, avoid the bandwidth where it's greater than 4% of the center frequency. So at 600 megahertz, we keep bandwidths less than 24 megahertz. As that bandwidth gets larger, there's more ripple in the band, and there'll be somewhat of a performance hit. Avoid the duplex gap to be less than 1%. So at 700 megahertz, that'd be 7 megahertz gap between the two, minimal. At 2.6 gig, we'd like to see at least 26 megahertz gap between the two. And then a figure of merit for the filter, which is the bandwidth, how wide the filter is, how wide the allocation is, over the gap of less than 4. And a couple of notes or points of merit is it takes about 6 megahertz to drop a good filter skirt at 700 megahertz, and it takes about 12 megahertz to drop a good filter skirt at 2.6 gigahertz to reject and interfere. You can violate any or all of these numbers, and as you do, then we have to get to more esoteric filters, to more boutique solutions, and it will force us more towards tunable solutions. One of the issues with tunable is if I've got a 40 megahertz block and I'm trying to tune to one part or the other, some of the operators out there want to do carrier aggregation within that block, and they want me to operate on both sides of it at the same time. And then that will force me away from tunable and force me to do something to cover both. Okay. Well, one other thing we've talked about is large duplex gaps. The chart on here shows cell size versus frequency. So basically, at 500 megahertz, a cell could be 1,000 meters or 1,100 meters long. And at 3.5 gigahertz, it's down to about 300 meters. So as much as the uplink and downlink data is disparate, it's never goes to zero. If you fire up YouTube and you're watching a concert or something and streaming data down, your handset is still firing messages back to the base, acknowledging the packets of data that is received, managing the channel, managing the link, and keeping the link alive. So both links have to be active and alive for you to receive data. If the uplink and the downlink are too far apart in spectrum, then it's going to seriously restrict the cell size because both of those links need to be active. And as you go up in frequency, your effective length of your cell shrinks. So potentially, if you've got large disparate groups of spectrum, maybe those should be candidates for TDD rather than trying to do an FDD allegation with a very large duplex gap. The other comment is we would also like to avoid, where possible, variable duplex gaps. So one of the things that's happened in our industry is the time it takes to certify and test and validate our products has already well exceeded the time it takes to develop them. And we've seen that as delays in getting some of the new bands out there because there's just not enough hours in the day or week to get all the testing done. And that's even taking advantage of automated testing that's running around the clock. As if we were to add variable duplex gaps in there where any uplink channel can be paired with any downlink channel, that would just explode the test time that we would have to go through in order to get the products to market and slow that down. And the result of that would be is the products with the highest volume would again get the time, and there would be an even larger gap between getting first products out and getting smaller quantities of products out. And thank you.
Thank you very much, Bill. Just a reminder, if you have questions, raise your hand or whatever you need to do to get a card and write it down for us. And also, I think we failed to mention during our introductions that my co-moderator here, in addition to his role at AT&T Labs, is also on our Technological Advisory Council, which is part of the group that's helping put this meeting together, because these topics are of great interest to the TAC. Just to follow up on actually something you said, Bill. So for Bill, you were talking a little bit about a passband restriction, 4%. So for example, if we're looking at spectrum at 600 megahertz, we couldn't be more than 24 megahertz in a single band, let's call it. Does that mean that in the FDD case it would be 24 plus 24, but in the TDD case it would just be 24? Right. That was short answer. No time to even switch the camera to you. So does that then mean, in a sense, well, I guess it's a trade-off. Then I'm getting more for FDD in that case. I can do 24 plus 24, although I guess FDD has an inherently more complex filter to start with.
And it's going to depend on what gap do you have between and what do you want to do with that spectrum in between the two as well.
I have a similar follow-up question for Steve, actually. You talked a little bit about a link budget disadvantage for TDD because you're not able to transmit all the time. Does that mean that in these highly asymmetric cases, if you're only transmitting uplink 1/8 of the time, that you have a serious uplink link budget impact?
Yes, Chris, that's right. If you're at cell edge, you're transmitting full power on a single resource block. And if that full power is limited, as we heard this in panel 1 today, it's limited to the same peak power level as with FDD, then the fact that you can only transmit 1/8 of the time means you're either transmitting 1/8 of the bits, and you've reduced your uplink bit rate, or you have to change the cell edge distance.
So it's not a disadvantage if your requirement for the cell edge performance is 1/8 of what it might otherwise be.
That's right. That's true.
Okay.
But
Does anybody
keep
else
in
on
mind
the
that
panel?
the minimum rate is the same as one resource block.
Right. So
You can't go less than one resource block.
So effectively, what does that mean? Can you expand on that?
I can't expand the band or the cell edge by going to a lower data rate than one resource block.
Okay. I see puzzled looks on the panel. Does anybody else want to comment on this topic? Peter, go ahead, Peter.
Yes, I agree definitely to the extent that if we allocated less uplink because we expect less uplink throughput, then in general we would be okay. So there is less opportunity to transmit, of course, but there are fewer bits to be transmitted. Having said that, if there are UEs that are very seriously disadvantaged because they are struggling with bad link budget, even the same number of bits, if we could, let's say in an FDD case, transmit all the time, with retransmissions, we could achieve a better link budget because with lower power, lower receive power, by combining, the base station could receive the same data. So I would agree nominally that it's not an issue, but once we actually try to extend the range of the uplink and really look at the worst disadvantaged UEs that happen to be in a very bad link budget position, then it still makes a difference. So FDD still has disadvantage that the UE can transmit all the time.
Okay, thank you. Thank you.
Let me pose a question to Al, and then for others to also think about. Are there any issues in the standards with supporting even more bands than are allocated today? I think a previous panel touched on that a bit, but I'd like to get your thoughts on that.
Yeah, it's an interesting problem. I mean, if we look at LTE, we've just seen a growth in adding new bands into the standard very rapidly. I mean, it seems like different operators, throughout the globe, if they've got spectrum, they're saying, gee, we'd like it to be able to support LTE and we want to add new band. And as we heard from earlier today, the devices and chipsets are being limited to, what were they saying, like 12 to 14 different bands. You start adding more and more bands, it's going to be very difficult to get devices that support all of these bands. And it also would be good if the bands could be more global, okay, instead of, gee, we've got this band for, the country of Morocco and this band for, the Philippines. And before you know it, you've got it so segmented and split up. And as you start adding carrier aggregation for those bands, and operators are saying, I want to aggregate my specific bands, you get devices that are targeted specifically for an operator, which could hurt the industry, okay? When I move from my device in the U.S. with AT&T and I go over to a different region, my performance is going to suffer because it probably isn't going to support the specific carrier aggregation bands in that other region. So I think that the standard can support more bands, but then the issue is can devices be implemented to support all of these new bands and support carrier aggregation for these bands. And that's where I see the real problem is going to be, Brian. Okay.
Thank you.
Of course, for AT&T, we'll make sure that we support them.
AT&T Labs. AT&T Labs.
Yeah. Anyone else care to comment? Erica?
Yeah, I would like to comment there because as we have heard before, and as Al said, I completely agree. There is actually no limitation to add a new band from the standard point of view. Well, of course, it will increase our working run for a little bit, but apart from that, it would not be any problem. However, I think that we should think about when we standardize a new band, we should think about just standardizing global harmonized bands, so we can actually ensure roaming and we can also improve economies of scale. So that's really something that we should keep in mind when we decide to just add a band.
So, as a follow-up to that, Erica, are there standards issues with adding a new carrier aggregation combination?
There is not really any issue on adding any carrier aggregation combination, but we have to think about which combinations we are thinking about. So there are combinations which are, well, we have heard that before. in the previous panel. Some combinations are easier, some combinations are more difficult. So of course, if you keep on adding very difficult combinations, then it will be more difficult to just support them from the UE point of view.
And each carrier aggregation
that's
pair,
Bill, by the way.
Sorry, each carrier aggregation pair is treated separately in standards and has to be dealt with and written separately.
So is that then an issue for the number of carriers supporting each combination? I mean, is it harder to get scale if you have a unique combination?
If you have a unique combination, it's harder to get attention, get it done.
And Peter, it looked like you had something to add.
I agree with the previous speakers that this is really mostly a device issue and device implementation issue. But there is also a standards aspect. But the standards committee can only specify a certain number of bands or band combinations in a given time. So there is kind of I would say, a rate limitation from what can be standardized to begin with. And if we keep on adding more combinations, then what that is higher, basically the rate of adding this than what can be actually processed, then we build up a queue. So there's going to be lots of these bands and band combinations that are known to be targeted, but the performance requirements would not be available for quite some time. And because of that, the components cannot be made for quite some time, and so on and so forth. So there is that aspect as well.
Thanks. We have a question from the audience, and we'll start this with Steve, and then if others care to offer their response as well. Could unlicensed operations be accommodated in a duplex gap or in a guard band? And if so, what rules should the FCC put in place?
There has been some of this in the middle of the PCS band. There is the unlicensed band that's used by some Bluetooth and wireless headset type products. So there is the precedent for that. So the answer must be yes, with some constraints. Having a guard band between an uplink and a downlink band is necessary to keep interference to a minimum. If there's interferers in that guard band, then there's a problem. And so those products that might operate in the guard band would have to be low power, such as Bluetooth is, or constrained in its where they'd be located, or what power they'd operate at, or how they're controlled by some spectrum sharing concepts. Hope that's to the point.
No, thank you. Does anybody else want to jump in on that? Al, go ahead.
Yeah, I think also you'd have a hard time getting device manufacturers to build devices that are in these niche areas, and if you don't have a standard to support the out-of-band emissions and spectral mask and specific requirements, I think you'd find it very difficult for device manufacturers to, support, these specific areas.
So you're talking about we should set technical standards for the unlicensed use.
I'm sorry?
So you're talking about the need to set clear technical standards for unlicensed use in the guard band if we want to do that? Is that kind
I'm not sure I'd do that. Okay, I'm just saying that I think you'd have a hard time getting devices to support these unlicensed spectral areas.
I think history doesn't agree with that. I think we've seen a lot of use of unlicensed spectrum, and if it's available, people will find a way to use it.
So follow up to Bill. I guess you were talking about duplex gaps of 1%, and Erica was talking about 10 megahertz between uplink and downlink. So in a lot of these bands, we're talking relatively small pieces of guard bands, 6 megahertz, 10 megahertz, 5 megahertz. Do you think that's enough for a unlicensed ecosystem, or do you think you need larger chunks?
I think I think it can be made to work. I think if you can make the gap larger, or the unlicensed piece of spectrum larger, so that Wi-Fi could fit in it as currently defined, that would be more useful. But I think whatever pieces are made available, they'll find uses for.
Can you remind us how much spectrum Wi-Fi uses?
Wi-Fi is currently in at least 20 megahertz channels. 40 megahertz if you use N.
Did anybody else want to weigh in on unlicensed? Erica?
I would just like to comment here because it seems that we are going a little bit the way of keeping guardrabands when we actually need them. So, of course, if we can use the spectrum in an unlicensed way, it could be positive, but we have to ensure that the license systems will still work. So we have to make sure that if we actually need a guardband, we have to keep it. And of course, if we can make use of it, it's much better. But I think we have to study what is the impact on the license spectrum as well.
If I may add
another go ahead, Steve.
To this. One thing that keeps me a little bit worried at night is that there are some spectrum planning rules that we've used in RF planning rules that have in the past presumed things like having our base stations on towers and the receivers with high sensitivity, high selective filters based in these large cabinets of equipment, and far distant from things like the PCS unlicensed band in the middle of the PCS band, being distance away. But as we go to small cells and placing base stations on utility poles or on the side of buildings or even on our desktops, if there's an H-block unlicensed transmitter there, the distance rules that we've used in the past are inappropriate. And so we do have a problem with small cells being, they can be placed anywhere, and the problem is that they'll be placed anywhere, even where they don't have the protections that we're used to from that the guard bands provided, even with unlicensed operations in them. So this is an area of some concern that we need to keep in mind. So those guard bands are even, we're going to get more jealous about making sure that unlicensed services don't cause us problems in them.
Thank you. Changing topics slightly. I know you haven't seen it for that long, but when I was talking during my presentation a bit about this idea that it's more important to have a uniform band plan for a device than a base station, does anybody have any reactions to that? Would you agree that it's feasible to have different base station filters in different regions of the country, for example, or that it makes sense to have if you have a band with exclusions, it makes more sense to make that an uplink band than a downlink band? Anybody want to take a stab at that? Peter? Excellent.
I think, yes, Chris, you made good points. Although, what is a band for a base station? I guess you meant receive for the most part. It is a transmit for DUE. So everything is always paired. If there is a particular frequency where the base station needs filters, probably DUE also needs a filter because it's transmitting. So, but I think the bottom line point is that for the UE, there cannot be multiple filters, or at least it will be too complicated or difficult to have multiple filters, for example, if there are overlapping bands, while the base station can just pick one that is actually fitting the actual deployment. So from that perspective, yes, there is a fairly big difference. The UE need global bands because it has a limited number of filters, and that filter has to work as many places as possible. On the other hand, the base station can build a custom design filter for each particular deployment. It doesn't need to cover the whole band, for example. I'm not saying all base stations are built that way, but at least that is a possibility.
Okay, thank you. To follow up on that a little bit, I mean, I think clearly if it's a receive band for the base station, it's a transmit band for the UE. I agree with that, but I think we also were hearing this morning that UEs can often meet the emissions requirements without a transmit filter or with only a harmonic filter. We heard that for TDD and for GSM, for example. And so if you had a receive filter, if you had a transmit filter on the UE that was the largest of the three regions, would it really be a problem with the UE having some spill in other regions where the transmit band was smaller? Looks like Bill really wants to jump in on that.
Yeah.
So, Bill.
We don't ship any phones without a transmit filter, and a big concern is the carrier aggregation and the other phones or the other radios in the phone. We have to clean up a lot of the noise and extraneous stuff off the transmitter. So it's PAs, filters, and antennas. Those are really the frequency sensitive parts in the phone. We'd have to look at each one case by case. I liked what you presented, where you had a larger receive allocation or larger downlink allocation than an uplink allocation. I thought that would be relatively easy to implement.
Peter, go ahead.
Yes, to your previous question. So I believe you mentioned the minus 43 dB requirement that might be possible to meet without a filter, but there are also coexistence requirements for the devices. So there is a big list of frequency range in which, let's say, for LTE, the DUI has to meet minus 50 dBm per megahertz limit. And unfortunately, these are dispersed, so there is not an easy way to deal with it unless there is a filter built in. So the emission has to be low enough in other band receive parts. And without a filter, I don't think it's feasible to achieve that performance.
So you'd say it depends on the coexistence requirements and what the other adjacent uses are then in that case?
Yes, some of this is actually a stated requirement in a specification, so we would not be compliant if it doesn't meet, and it lists a whole number of bands. For each operating band, there is a bunch of protected bands that are expected to operate in the same area.
Right, I agree, but traditionally 3GPP, the protected bands are the other 3GPP bands. But if this was another service, then you'd have to look at the requirements of protecting that service, right? I've heard we have 2 more questions on the way. I didn't want to start a TDD-FDD war earlier, but maybe I did because we got the following question. If TDD has a link budget advantage from not being able to transmit all the time, isn't that also a battery life advantage?
Yes, it is.
Yeah. So, yes, everybody agrees, George. Thank you.
Okay, the next question. As a follow-up to the questions about unlicensed services in the guard band, could licensed narrowband services such as wireless microphones possibly be accommodated? Anyone like to address that?
Could you read it again?
Okay.
Just we have licensed wireless microphones, but they're very narrow band. So the question is, could very narrow band operations be placed in one of these guard bands or duplex gaps, even if they're relatively higher power? Peter?
Everything is possible, I think, but in this particular stated case, I think maybe the most worrisome case would be there is this wireless microphone that happens to be close to a device that receives its own downlink, and maybe its own downlink is relatively weak. And in this case, although it's narrowband, so good filtering could be done, but it's really a significantly high power. And the device filter, actually, it was shown before in the duplex app, doesn't really do too much. So that means that this very high power signal will get into the receiver. And although it could be filtered out later at a later stage, but by that time, because of nonlinearity or saturation or whatever other issues, it already interferes with its received signal. So I think if this to be done, then there has to be some way to make sure that the two devices cannot be close to each other, which is by default very difficult to do. Otherwise, there has to be a strict power limit so that the interfering device is not going to be saturate the receiver before it could be doing any filtering. Thank you.
Thank you. Anyone else want to jump in on that? Oh, we got another audience question here. Well, whoever wants to take this one can. It says, this is a follow-up on guard bands. It says, small cell FDD deployments place base transmitters close to adjacent band mobile receivers. Isn't that an interference scenario similar to the different mobile-to-mobile scenarios that affect TDD systems? Does that question make sense to anyone here? Sure. Small cell FDD deployments place base transmitters close to adjacent band mobile receivers. I guess that's actually the part I'm confused by. And then isn't that similar to the mobile-to-mobile TDD scenario?
Yeah, there's the near-far problem when you have base stations that used to be, tens of meters away at the top of a tower are now placed maybe on your desk, and so the dynamic range needs to be controlled to allow comparable operational modes. And there is this near-far problem that small cells are introducing, and one way to handle it is to restrict their transmit power accordingly. But that you can get within millimeters, so it can be a problem.
Okay.
It's being addressed in standards, I think, but it'll take some time.
Change of topic again. We talked a lot about using carrier aggregation to support asymmetric FDD, but it sounds like maybe that's not the only way to. Is that the only way to support asymmetric FDD in the standards, or kind of Peter was saying there's a lot of openness in the. Erica, do you want to address that first?
Yes, I guess there is. You can think of asymmetric FDD in two ways. You can think about carrier aggregation, and you can think two downlinks and one uplink. Of course, there we have asymmetric FDD. You could also think about asymmetric FDD in a single operating band, but that would require variable duplex distance, and that is currently not specified on the standards. And as Peter has mentioned before, it could be a little bit tricky from the product point of view. So it has a standard impact, and it will also have some product impact.
Thank you. I think we're almost out of time, right, Cecilia? Yeah, so just for all five of you, are there any last points you want to make sure you make to the FCC before we close the panel? Or to the TAC, for that matter? Al, anything you want to say?
I think I already touched on this, but I do believe that if we could try to ensure more global alignment on spectrum, that would be key. I mean, as we've already said, you have problems supporting a number of different bands, and we're seeing just a great boom and growth in new bands and carrier aggregation. And I think until we get to the part of having a truly software-definable radio, it would be good if we could try to look more towards global band usage.
I've been trying to take read the mind of FCC staffs and so forth, and I've been getting these images of an auction that includes a way for the operators to bid on where the division between uplink channels and downlink channels might end up, say in the 600 megahertz band or something, and I see that there's inevitably going to be some greenfield operators that are new entrants that will want to have some uplink along with their downlink. So there's always some need for paired spectrum, if for no other reason than the fact that uplink traffic is also growing exponentially, just from a smaller base and not quite as fast as the downlink traffic. But where that division might end up happening seems to need to be constant throughout the nation or throughout a standard, so that terminals don't have to have different duplex filters with different transition points. But I think the image seems to have some currency to it. I think it's a nice concept if it can be done with a common nationwide or global place where that happens.
Very interesting idea. We'll call it the Wilkes Band Plan if we do it. Peter, anything you wanted to say before we close?
Yes, thank you. I'd just like to emphasize the answer to your last question. So it is well known that there is an asymmetry between downlink and uplink, and it is predicted that it's going to stay that way for a long time. And it's very, very useful to find solutions to address this. And it was mentioned in your question as well that there are two different ways to do this, either defining asymmetric bandwidth or to carrier aggregation. And Corrugation is something that exists today, so we can already address this problem, so we would like to point to that direction. The other case needs some performance work, and it might be some time away.
Okay, thank you. Erica?
Yeah, maybe three different messages for the FCC. And one is to consider global harmonized bands, as we have said before. I think that is very important, especially from the device point of view. And also that we should consider coexistence issues when allocating a spectrum to make sure that there is enough separation and that both systems will actually work. And the third remark that I would like to make is to consider large blocks rather than small blocks.
Okay, thank you. And Bill, you can be the last.
I'd like to reiterate Al Jetty's point. If we can get more globally allocated spectrum blocks, that would definitely help get economies of scale onto those solutions.
Great. Is anything else? I think, Brian, anything you want to add? Okay, thank you, Cecilia.
If we could get the panel members for the third and final panel to come forward, please. So as a reminder for those watching remotely, if you have a question for the panelists, you can send an email to livequestions@fcc.gov. And if you're sitting here, just raise your hand and we'll bring you a note card and a pen and get your questions from you. Our third and final panel for today is Network Operator Perspectives on Band Plan Design. We have two moderators for this panel. Tom Peters is the Chief Engineer for the Wireless Telecommunications Bureau here at the FCC. And Brian Markwalter is the VP of Technology and Standards at the Consumer Electronics Association and is also a member of our Technological Advisory Council here at the FCC.
Thank you, Cecilia. As Cecilia said, I'm Tom Peters. I'm the Chief Engineer in the Wireless Bureau. We've had a very interesting day today, I think most would agree, starting with the component vendors and getting closer and closer to the consumer end of the supply chain with the infrastructure vendors that you just heard from. And now we're going to have the grand finale where we hear the operators' perspectives on some of the concepts regarding band plans that you've heard earlier today. So I'd like to first thank our distinguished panelists, and I will introduce them to Brian's left is Tom Swanabori. Tom is the Vice President of Technology at Verizon. To his left is Doug Hislop. Doug is representing the Rural Cellular Association, an association of some of the more rural, smaller operators in the United States. To his left is Iyad Tarazi. Iyad is Vice President of Network Development and Engineering at Sprint. To his left is George Harder, Director of Access Development at Clearwire. And finally, last but not least, at the end is Dan Wilson. Dan is a Principal Engineer at T-Mobile. Thank you all for coming. As in the last panel, we sent each of our panelists a question that we thought was relevant to the discussion, and we asked each of them to respond to this question. So I will start with Tom Swanabori of Verizon. His question was on the symmetry and asymmetry of band plans, an issue that was discussed in great detail in the previous session. The FCC has traditionally designed its FDD band plans to be symmetric, partly driven by the fact that voice traffic is largely symmetric. And as we've heard earlier today, changes in technology and traffic patterns suggest that in a data world we may want to revisit this assumption. How do you as an operator think about the relative value of uplink versus downlink downlink spectrum? And should the FCC attempt to address this traffic asymmetry in future band plans? And if so, how? I would just add, from the previous session, Mr. Steve Wilkes of Alcatel-Lucent held up a graph that showed how purely asymmetric data traffic is. But one interesting thing about that graph is that it seemed to be trending downward. The numbers are still quite high, but the trends seem to be coming down, and I'm interested here, an operator's perspective on how they feel about that asymmetry and how it affects the value of spectrum.
Okay, good. Thank you very much, Tom, and I'm pleased to be here. Thank you very much for the opportunity to address the FCC and the TAC, and to be able to share some ideas with you here on the topic. So first of all, I wanted to put up in the first slide and kind of show a little bit about the global data forecast, because it's important background, I think, as we think about future band plans and how they will evolve given where we are today. And this is actually a chart, a Cisco forecast, and it's actually in a unit of exabytes, which I admit I had to go look up, which is actually 10 to the 18th in terms of bytes over the next 5 years or so, with about a 70% cumulative aggregate growth rate. And you think about where we are today, and we've all been talking about the growth of mobile data and how it's been evolving, and even though it is asymmetric today, in large part, there's a number of applications, I think, and devices that are changing. So up until now, mobile data has been largely driven by the use of laptops, smartphones, and most recently by tablets and the associated applications that are going on those. But if you look at another forecast here of some of the different mobile application growth, I think it provides some insight. So, it's probably very hard to read there, but mobile VoIP is the top one, and it's actually very, very small, less than 1%. Over time, it's expected the second one, mobile gaming, will grow more and more. File sharing will increase. M2M is something that I'll come back and talk about just a little bit, but I think machine-to-machine is something that's just starting to become more prevalent, and you can see that today in energy, telemetry, telematics. But I think if you heard some of the speakers this morning, they're talking about things that are in healthcare and other areas where you could see dramatically more uplink and downlink bandwidth needs. When you think about mobile web and data, I think that's what's been driving most of this so far. And then, of course, you've got mobile video. And I think we traditionally think about mobile video primarily being in the downlink by the consumers, watching YouTube, actually now today you can watch all kinds of video that's been put onto the web. But I think you can also think about other new applications where you're going to be uploading more and more pictures. There's more and more video being uploaded and so forth. And that could be done also probably in real time. So when you think about where we are today, there's a lot of different applications I think that will change. And somebody referred to it on the last panel as though it could be applications that get invented in the next several months, years, and so forth that will change. So we need to be flexible in that regard. And we at Verizon, I think you're aware of deployed LTE, and we've got some experience since 2010 when we first launched it. And we've got over 2/3 of our POPs covered over today, and intend to cover the entire footprint by the end of next year. So other operators, again, are also moving to this in the U.S. and around the world. Also want to think about, as important as we think about band planning, that it was very insightful for the FCC to be thinking about 700 megahertz band several years ago, and 5 years ago when the auction occurred, and have the foresight to be able to clear that band and make it useful and available to us as we're utilizing it today. Also, to be working on things like band plans with adjacent neighbors. So I know you've been helping us with Canada and also with Mexico, and it's been very helpful because it's important that we align these band plans and get as much global scale as possible. So if we think about the standards and some of the asymmetry questions that you mentioned, Tom. It's we think that the flexible bandwidth allocations do give us some opportunity. So as we look forward into the next set of bands that'll be allocated, that asymmetric is something that we might want to take advantage of as an industry. That downlink probably is more important than uplink, but we need to be flexible. One of the ways we think about it is more about having supplemental downlink with an existing paired set of spectrum as opposed to another way to do it. And I think we also need to keep in mind a lot of things were mentioned in terms of devices and complexity, but devices are limited today also by the technology and also by their transmit power. So inherently, there's probably a little less uplink data being transmitted relative to what there could be. Carrier aggregation is one way to be doing that we have basically in standards that's being in development today and should be here within the next year or two. So you'll see that in terms of peak speeds and greater overall capacity, I think is important. So we think about both. And then there's also one thing to keep in mind in terms of the standard, which is the broadcast technology is available. So it's actually in the standard, and it's available for something if we're thinking about how to utilize mobile video. There's other important things. In general, I think you want to keep the band plan simple, minimize the complexity for some of the devices, and keep in mind that a lot of us are already supporting many other technologies and bands. So while there are increasingly capable more and more bands being able to put in devices, we're trying to do that with our existing technologies and also support some global roaming. Things like multiple input, multiple output MIMO are already being supported in devices. That adds to device complexity. People are talking about higher order MIMO, carrier aggregation. These things all add complexity and cost to the devices. And for operators, device subsidies are a challenge. So just in summarizing, I do think that asymmetry is an important aspect to be thinking about. The standards, I think, allow us to do some things like that. We want to be able to be realistic about what technologies are in their relative maturity, and we want to have practical solutions we can implement over the next 5, 10, and 15 years.
Great, thank you.
Let me tee up this one.
Yep.
All right. Thank you, Tom. So I want to raise a question about the geographic allocation of spectrum here. This will be directed to Doug. So the Commission has tried as much as possible to allocate spectrum on a nationwide basis so far. That's and obviously we've heard a lot about scale and driving economy of scale, so that sort of goes with it. Value of things go up the more the more usable they are. But that's going to be harder and harder to do. So Doug, I'd like you to comment or speak to what kind of factors the Commission should think about as it finds spectrum and what looks like it's going to be in smaller chunks and maybe not allocated across the whole U.S. uniformly.
Thank you, Brian. I'd like to start with pointing out with where we're at today. If you think about the PCS band, it is nationwide spectrum split into several different blocks. We'll go ahead and skip to the first real slide. So the ownership within any given block is actually spread among a number of operators across the country. So any one block is owned by many different people, different parts of the country. As an operator, one of the nationwide operators would have acquired ownership in many of the different blocks in different geographies to put together the nationwide PCS system. So today, it's a great example of how a system can be built using spectrum which is not contiguous geographically. Now, what helps to make that such a great success story is that the spectrum itself is available nationwide, and that fuels an ecosystem behind it. All of the operators are buying common equipment which works across all of the blocks. So scale is there for devices, and interoperability is automatically built in because the equipment works across all of the blocks. So looking ahead to the case where spectrum may not be available nationwide, in a way the problem is similar. We'll have blocks of spectrum that are geographically available in different portions of the country. So it becomes a question of really two questions. One, you need to make sure that those different blocks fit rationally within some kind of a band class, as we heard earlier today.
so that equipment can be built within a band class which will cover enough population among those geographies so that you'll have scale. And then equally important, make sure there's some plan for interoperability among the different blocks. So within a particular geography, if you have multiple blocks that you have auctioned, you want to make sure there's an incentive there that any equipment built to cover all of these different blocks in a band class would, the device would support all those different blocks. You minimize the number of band classes for a new spectrum coming out. So some things that will help with that. Band planning, it's important to think about the uplink block and the downlink block and how they work together. So uplink blocks really can be non-contiguous in spectrum. From the base station perspective, as the earlier panel mentioned, you can have filters that are built to cover particular receive blocks. On the device side, the transmit filter in some situations can be relatively wide, depending on the adjacent services, because the emissions mask in these modern technologies provides a reasonable level of protection for nearby operations. Downlink blocks may also be non-contiguous to some degree. The commercial device receivers today, as mentioned in the earlier panels, there are many factors which are driving increases in linearity of the components, so the receivers are really quite robust. They do an excellent job of performing well in the presence of strong nearby signals. A consideration which would encourage more contiguity among downlink blocks would be trying to make sure you leverage the efficiency of the power amplifier in the base station. You don't want too small of a block spread too far apart from other blocks and drive up the cost of your base station. So really the success of non-contiguous spectrum allocations depends also to a great degree on the type of operations which are interleaved. So if you can keep similar transmit directions among different services, they tend to be compatible. Dissimilar directions require a more detailed look at the coexistence criteria. Thank you.
Great, thank you. Next question is for Iyad. We've had a lot of discussion today about block sizes in future band plans, and wanted to get an operator's perspective of how we at the FCC should think about the optimal block size within future spectrum bands, especially when we're potentially reclaiming spectrum in smaller chunks, for example, from 6 megahertz TV channels, as would be the case in incentive auctions. Should we be considering a building block approach where we license in smaller blocks and allow operators through either technology or through auction mechanisms to aggregate that spectrum into blocks that would support wider channels? Can you give us your thoughts on that?
Thank you. Can you get the slides up, please? I tried to take an approach of an economic and operational view of the spectrum. We had a lot of discussion earlier today about the technology view, the art of the possible, the development of devices, and so on. But especially for a carrier like us that strives to maintain specific marketing messages and a certain value proposition, the most important consideration ultimately is the scale and cost that comes with it. And most carriers around the world right now define their scale as finding more than one carrier versus being really good at their own plans. Obviously, there are exceptions. There are very large carriers here in the U.S. that can drive the ecosystem, but a lot of people like Sprint will need a global ecosystem and even in some cases a national ecosystem to ride on. So most of the considerations for spectrum block sizes ultimately is about how do you use these type of considerations. When can you get access to the spectrum? How do you use it? How do you align it with the current spectrum? How do you align it with the global spectrum? You know, what technology to use, and not just technology for the promise of technology, but also what's practical in terms of cost and performance trade-offs that you can do. So next slide, please. Oh, I'm sorry. Yeah, I thought I'm getting some real support here. No, I'm just kidding. The next slide. So the first, probably and most valuable way of doing this, in the absence of large new blocks, which we talked about 600 megahertz here, it really is to extend existing spectrum blocks so that you can build on top of the ecosystem, especially for devices and for base stations. And that's what Sprint did with Band Class 25 to extend the PCS spectrum. It's not just only important for LTE, but also if you look 10 years down the road, eventually you would expect that there'll be conversions of existing technologies to LTE. And so we tried to do that as well with 800 to go to Band Class 26 to find additional operators and additional ranges, because the more you build a promise for the future, the more you build that. The other thing that would be is really essential for us is more harmonization of global bands. As hopefully you'll hear my partner here from Clearwire talk about Band Class 41 and how the environment is completely different when you have a band class that has some more harmonization, because ultimately it's a scale business. Our manufacturers are global. Our problem statements are global. And while the U.S. leads in many aspects of this technology, more means cheaper and easier and so on. So that would be a big consideration. It's not very obvious to me how you would do that. I'll be the first to admit. But at least in future bands, maybe at least clarifying an intent and try to build support internationally may be the best way to do that. The other discussion about implementation flexibility, and I think Tom touched up on it, another touched up on it. I think there are some minimum things we need in terms of making sure that we end up with national, global, just even at least national coordinated way of how to use these new blocks. But ultimately, we do need some flexibility in some of the way we're using some of the spectrum now. For example, what we've done in Band Class 26, where we're using some for CDMA, some for LTE. We're creating some of our own, guard bands that may be different in slightly different areas, and maybe eventually we'll recover all these guard bands. That flexibility is really essential, especially if you view the world as not black and white, but is in a transition state. Because I view the world more as you're here and the future is there, and it's all about economies of transition to LTE, not just about starting over. And building brand new assets. And to the degree you're trying to preserve the value of existing spectrums, then you need a little bit of flexibility around how to manage that in order to create not just incentives for harmonization with the new spectrum, but also harmonization for conversion of existing spectrums. And then in terms of block size, sort of the simplest way of answering the question, I think smaller is better if we get access to it earlier and able to build on it. But we also need sort of plans of intent to say, here's how we want you to build this, and incent carriers and operators to do it in a way that allows for aggregation of that spectrum over time and allows for us to be able to make sure we don't trash each other in the process and in the laws of unintended consequences sort of thing. With that, let me turn this back to you.
Thank you.
Okay. So we want to take up the subject of flexibility, and the FCC has worked hard at sort of a flexible use policy, at least with respect to like TDD and FDD. So there's a question here as to whether too much flexibility is potentially a problem, which seems odd since we normally would want the marketplace to decide as much as possible. But we've also had a lot of discussion about the standards and certain things like components not moving until standards are done. So is there the potential that if the FCC is not specific enough, then the industry doesn't know how to move forward, and so there's no foundation to build upon? And George, I don't know if you can speak to that question about how much flexibility is the right amount in band allocation.
So I'll take on the role today of being the advocate of flexible use and also being a TDD advocate in a sea of FDD users. Clearwire supports the FCC's flexible use policies, and I think in many ways we're a poster child for that policy. And I'll give you some examples of how that manifests itself. But we think that allowing operators the flexibility to choose an appropriate technology to meet their business needs is an important tool to have in the toolbox. Also, allowing those same operators to have the ability to work with other operators in making the flexible use work is another key component of that. Operators need the ability to be able to examine device ecosystems, to be able to look at network infrastructure, look at availability, at timing, features, functionality, and to choose what best meets their needs from a business standpoint. Global utilization, global harmonization is key. It's absolutely key, and I think Clearwire has been a big advocate of that. Again, it's all about giving an operator the flexibility in terms of the spectrum that he has to also blend that with the business goals and with device ecosystem and network infrastructure to make the proper choices. Obviously, though, flexibility is very dependent on the amount of spectrum, right? If you don't have a lot of spectrum, it's hard to be flexible. I mean, if you're only able to achieve minimum speeds, minimum capacities, it can be difficult to be flexible. However, because of the FCC's flexible use policies, Clearwire's been able to entertain changing technologies in midstream. I think a lot of you are probably familiar with the path that we've taken historically. We actually started out with a pre-WiMAX technology that we deployed. Then we stepped from that into WiMAX, which was, both of these were TDD-based technologies, but dissimilar. Different in terms of TDD ratio, different in terms of frame structure, just completely different. But because of the flexibility that we had and the spectrum that we had, we were able to make them work. As we grew and progressed from WiMAX to LTE, we also had another option. We actually had the ability to consider TDD or FDD. Because of the way Band Class 41 is structured with 38 and 7 in the middle of it, we could honestly sit back and take a good hard look at that and decide which one is appropriate for our business needs. Ultimately, we came to the conclusion that TDD was the right choice, some of it because of our legacy WiMAX deployments and the things that we could do with existing equipment, the existing technology that was up there to efficiently deploy LTE, but we had that ability because of the flexible use policies. I think the other point I'd like to make is that Clearwire is able to coexist with other operators even though there's flexible use within the band. We have market deployments where we have immediately adjacent operators in the market. We also have co-channel operators that are adjacent to our markets. And we're always able to coexist and to figure, to go into the coexistence tool bag and through filters, through guardband, through synchronization, through all of the techniques that engineers have available to them to make it work. So I think bottom line, Clearwire is supportive of flexible use as well as TDD.
Totally unexpected. No, thank you. Last question for Dan relates to sort of a similar theme of spectrum flexibility, but specifically here we're asking about homogeneity of spectrum blocks. That is, recent experience has shown that for a variety of reasons, two similarly sized blocks in a given spectrum band may in fact turn out to have very, very different characteristics in terms of their interference, usability, due to their proximity to other services. So how should we think about, in the future as we design new band plans, how should we think about this issue, such as when we're thinking about determining block sizes, the size of duplex gaps, and guard bands? We've had a lot of discussion about guard bands and whether or not the FCC should, as is done in some other parts of the world, say we believe you need a 3 megahertz or a 5 megahertz or whatever it is, guard band between the edge of your mobile broadband spectrum allocation and an adjacent service. how does an operator think about those trade-offs between maybe certainty, the creation of homogeneity of blocks, versus the usability of spectrum? Dan?
Thank you, Tom, for the question. In terms of homogeneous spectrum blocks, we certainly think that it makes sense in a lot of cases. I have a couple of points to go through to answer this question. I guess the first question, and this has been mentioned, the first response I would have here is, and this has been mentioned in panel 2 and also by a few of the panelists here, is that given the broadband technologies we see, we would like to see a minimum of 5x5 paired blocks. Anything less than that doesn't really make sense given today's UMTS and going forward with LTE. We're seeing 5x5 and 10x10 blocks largely being deployed, which makes the most sense. So anything less than a 5x5 block wouldn't make sense, and it would be a difficult thing for us, and I think most operators. So given that, I think, though, as we look at the PCS and the AWS bands, those blocks on the band edges have typically been larger than the other blocks. Typically with the PCS, the A and the F blocks, A and C blocks in PCS, and in AWS we have the A and the F blocks have been 10x10 blocks, which has been extremely helpful, if you will, as we've worked mainly, and I've worked extensively with the BAS licensees in the A block, as T-Mobile has deployed quite a bit of that A block spectrum, and that's been a helpful thing to have a little more bandwidth there to work with non-mobile operators, with other entities that have different service rules and different operation standards. So that I think that's important, that band edges be given additional flexibility, as they will have some other coordination efforts that will be important for them as they deploy their networks in those blocks. Moving on to the duplex gap question, we think that it's important to keep those consistent, and that was mentioned in the second panel. Variable or dynamic duplex gap, I think, lends to some difficulties, as was mentioned by some of the hardware vendors that discussed that in panel 2. One example there is AWS 3 and its potential pairing with 1755 Plus obviously would be advantageous for us, in that AWS 1 is just immediately below that and would be an extension of that. And so that hardware is in place. So some time is needed to study that and understand what additional costs might be there if the duplex gap would be increased from in AWS 3 as opposed to the 400 megahertz in AWS 1. So those are some of the first thoughts I have. In terms of, as I go back to adjacent channel coordination between industries, we feel strongly that the FCC should let the actual deployed technologies dictate what those out-of-band emission masks really are and what those guard bands should be. I think there's a chance there to set an inappropriate guard band and possibly waste some spectrum, when in reality we learned earlier this morning some of the advances in filter technology, which we have been able to take advantage of with broadcasters, as we've done in the AWS block. Initially, that was a difficult situation that did not look to have a good solution, but in fact we were able to find filter technology that made that work both for broadcasters and for T-Mobile UMTS deployment. So I think that was a good lesson. I think the out-of-band emission masks were appropriate and don't need to be made more stringent unless there's actual technical data, I would say, in the lab and in the field that support that. So I think that's an important thing to investigate those things and leave the band plan somewhat open for investigation work to take place. I think the last point I'll make, though, I think we need to obviously find a balance there. As technology, as we've learned today, I think technology cannot overcome poor band planning. And in some cases, we've seen the interoperability issues in 700. There's some difficult things there that don't look to have quick solutions. So I think we we need to continue to look into that, and I think that's what what today's time has been extremely helpful for us all to see that. So, thank you.
Great. Just a point of clarification on what you said about allowing industry and operators to determine the block sizes. Are you suggesting that, to determine the size of guard bands, are you suggesting that, for example, the FCC should auction maybe an 8 megahertz block that's directly adjacent to a service and allow the operator to determine how much of that to internalize for guard band versus saying this is going to be a 3 megahertz guard band on a 5 megahertz block that will auction the 5 megahertz block and leave the guard band unused. Which side of that are you suggesting?
Probably stay in multiples of 5 by 5 without specifying, exactly what needs to be there. I guess, in depending on what the adjacent use really is, that may or may not be appropriate. But I don't know that an extra 3 megahertz makes sense in some cases, especially with the filter technology that we've seen advance. That's how I would answer that. Yeah.
Okay. Thank you. Let's go back to the asymmetry question, because Tom made a statement earlier today. We talked about two different ways in which asymmetry could be implemented. One was, to have paired spectrum and then unpaired, say, downlink only spectrum that you would then aggregate. The second option was to maybe auction smaller uplink blocks and larger downlink blocks to achieve that sort of FDD asymmetry. And I think Tom made the point that he would prefer the former option, and I wanted to get the other panelists' view on their preference and thoughts on that. Doug, do you want to start?
Sure. Yes, that's a good question. Actually, I'll let you. Think about that for a minute.
I think in general, flexibility is better. I think that so even instead of specifying what's uplink, what downlink, and what's bigger and smaller and all of that, if you look at, and I do that often, look at what applications are using the network today, and put an age on them. My daughter is 10 years old. Every 80% of the network use has been invented since she was born. So if you actually go back and look at what people use the networks today and what they'll use it for the next 10 years, I really don't believe that we can truly be so prescribed about the ratios and how to use it and all of that. We do have to have some rules to make sure we don't trash the spectrum in the process of keeping it that flexible, but some flexibility instead of prescribing small uplink and a lot of downlink and here's what spectrum you should pair up with existing downlinks versus spectrum that's truly new, and what's FDD and what's TDD. And all of these things, in essence, are symptoms of overprescription in the end. I mean, in my personal... Now, again, there are reasons you would do that. But generically, to the degree you take some of these rules away and let the operators and the technologists that you heard from today make the most of the spectrum, there's a value there.
So you agree with George that flexible use is a good thing?
Yes, I would.
We should maintain that policy.
Yeah, I would. I mean, we have to figure out as an industry how to manage the adjacent spectrum issue. But to the degree we can open up, if you look at the 700 spectrum or the 800 spectrum we have, where if people imposed a lot of guard bands on us, it only would have been a 5 by 5 versus we're getting a CDMA channel out of it. That's a good example of, even if it's a 7 by 7, and you can do more of spectrum if you put it in operators' hands and give them a little more flexibility. We just have to figure out some trade-offs of how not to interfere with each other, really.
George.
Go ahead.
So, yeah, I very much agree with what Iyad has to say. In addition, as I look back over our network, we see the same trends, the uplink downlink ratio, heavy downlink. We saw the ratio quite large, and it's trending down over time, but we don't know what we don't know, right? As it continues to move, as it continues to evolve. From a TDD perspective, for Clearwire, we've kept our asymmetry ratio constant, and also not terribly heavy on the downlink. Partly because we see this trend, we know that uplink coming, but there's also the flip side of that is there's a link budget impact as well, right? There are other issues that you have to consider. There's things you don't know. There's link budget. So I think we agree. Leave it flexible. Leave it up to the operators that they can determine what best meets their needs.
Okay. Dan, did you have a comment?
I agree with that as well. I think we obviously would lean towards the FDD model, but the flexible use is crucial. I think the operators drive absolutely the most efficient use of spectrum, and I think we've proven that over time.
Okay. Did you have a question?
Well,
back to Doug. Sorry.
I'll weigh in now. I had a little time to think about that intricate question. There's just a lot of moving parts to this one. If you think about whether you're going to do a 5+5 with a separate 5 or a 10+5, the 5+5 is arguably more beneficial for small carriers. It gives them a more discrete size to acquire at auction. The separate 5 is arguably of more value to an entrenched operator who might have other spectrum they could aggregate that with.
That's a good point.
One other comment?
Oh, absolutely.
We are, at Clearwire, a big advocate of carrier aggregation as well. So if there are chunks that don't seem you can be quite flexible on, we still think having those allocated and being available to operators to use as carrier aggregation is a very powerful tool. So.
Great. Thank you.
Well, I was going to kind of change subject a little bit.
Absolutely.
So it's pretty clear now that we're on the third panel, it's a complex ecosystem here. So my question is around how you do planning. I mean, you interact with your vendors, and specifically, so as the FCC goes to auction more spectrum, you've got to be able to react to whatever rules come out. How much time? I mean, how do you interact with vendors, and do they then go interact with the component suppliers? And how much time do you need to figure out the complexities of rules of an auction? And so just if you could comment on that, what you need in terms of carriers for reacting to new auction becoming available or new spectrum becoming available.
I'll jump in as much time as possible. As a matter of fact, our number one job from a work perspective is to figure out how to thread the needles between what we're doing and the rest of the globe is doing. People can build you anything, but it's not economic about 80% of the time what you ask for. It's very, very important. There are a few people that can do that can move the needle for everybody else. But specifically for Sprint, it's very, very critical to riding somebody else's ecosystem. And that means that to the degree the rules are known in advance, we're able to work with other carriers around the globe to harmonize strategies, or even if it's not the same band, are we following the same device strategy? Are we following the same chipset strategy? It's very critical for a carrier of our size that we've been given plenty of time to harmonize the strategy. Otherwise, building it ourselves will be way too expensive and may not make it economic for our size of a carrier.
It's that it's important to have the right time, but it's also to understand kind of the parameters you're thinking about. So, when you are doing future band planning, as you're considering this, if you know whether you're going to be grouping downlinks together, for example, that helps us because we do our own assessment with our own engineers that both work kind of on the infrastructure side and the device side, and then we'll also consult with some of our suppliers to kind of see what we think some of the key issues might be and to see, have them validate that. And, that would help us influence our decision making in terms of what bands might we be interested in, which ones might be more problematic or challenging.
Thank you. Any other thoughts? Okay. Let's jump to another common theme that we've heard throughout the day is global harmonization. and the benefits of creating a band plan such that operators within that band plan can benefit from global scale. I wanted to get some further thoughts on what steps each of you think the FCC might be able to take as we, for example, clear some amount of spectrum in the 600 megahertz band through incentive auctions. How might we go about ensuring that we do it in such a way that it's accepted globally and has the potential in the future to become a global band with those scale advantages? Any thoughts on that?
Sure. Yeah, it is tough being on the leading edge as the U.S. was with 700 megahertz. And part of what we're seeing now in other parts of the world is in Asia especially, they're looking at it and defining 100 megahertz as a separate band class from what we did here. And so we end up having, it's driving a diversity of band classes in the equipment such that there's going to be difficulty in getting a global 700 band put together into the same device just because of the diversity of band classes required. So going forward, to the extent practical, other countries may not be as far ahead as we are in terms of what that would look like going into these new bands, but reach out, talk with them about where their countries are, what their spectrum is used for, and see if we can drive more commonality and match up better with the global allocations.
I would second that. I think it's more of a find a big enough block, which you may have here with 500 and 600, and then just announce the intent to the world so that people know it's coming, and then that actually gets the process started. It's when we come in very last minute with a small block. It's very hard to rally the globe around it, but if you want to rally the world, you have to have a bit of a leadership position on a very large block and give it plenty of time to sort of stew in the normal process of international relations, and also budget the time and energy and the staff resources to actually engage in the right places internationally. There's about 3 or 4 areas you'd have to engage in. You can get most of a global ecosystem. You don't actually need to talk to 200 carriers. There's about a couple of carriers in Asia that influence almost all of Asia. There's about one format and one supplier in Europe that can probably get you about 60% of the ecosystem in there. And I think you can fill in most of the dots there. So just a little bit of staff time, and time that might get you a lot of bang for the buck.
Great. Any other? George?
Just kind of a side comment. Clearwire is an advocate of the 2.4 to 2.7 band as a global band. I think if you look across many countries, you'll find frequencies that are in that band that are there and available for use as harmonization.
So, shift gears again a little bit. Another common theme of the day has been carrier aggregation, and certainly it's a technology where there's a lot of very active development work, promises to have benefits, but also at some cost of increased device complexity, the need for multiple receivers, for uplink carrier aggregation, multiple transmitters would be needed. All of these things potentially impact the device cost and performance. And with all the different combinations of bands that are available or that are needed around the world, and combinations of channel bandwidths, carrier aggregation gets to be rather complex. And I wanted to get an operator's perspective on the trade-offs between the benefits of carrier aggregation and the costs that it would have on your future business plans. Anybody want to jump in on that? Tom?
I'll start.
Okay.
We're still studying carrier aggregation. It's in active, very active planning, and we do feel that it has a place. I mean, we don't have that today, but we're thinking about where it might make sense in terms of peak download speeds and also increased capacity, and also, as I mentioned earlier, the supplemental downlink possibilities. So, kind of looking at all those, I think we still are evaluating, frankly, the cost implications of that and the complexity. So we need to understand that, but we're very active in that right now and trying to talk to device suppliers and see, what is the advantages of this versus doing other things, and how does that impact time to market and some things like that. So I think you'll see, we'll learn a lot more over the next several months as we continue to do the detailed planning around this.
We're in a similar position. We're evaluating. I think maybe my only caution is to rely on carrier aggregation to drive future spectrum allocation. It's too early for it to be used as a tool to simplify the spectrum problem. It's very different if you already have the spectrum trying to make the most of it versus if you're trying to say, let's use carrier aggregation as a solution for how do we simplify auctions, or I think we might be a year or two away from really understanding carrier aggregation in terms of performance and cost and availability and so on.
I totally agree with that, and I think, given that's where we support the FDD model going forward. I think it gives us the flexibility to do that as we understand those costs and those benefits.
Just going to add a comment about the device cost, and just keep that in mind that you need to look at the cost of the entire network as well. That by increasing the device cost somewhat, you may actually be driving down your cost of ownership on a per megabyte basis by saving on capacity sites.
One thing I didn't mention, Tom, is that some of these devices might be different. So you might treat certain devices you'd want to have carrier aggregation, and some others you might choose not to. So that's just something that to think about.
Great. Another potential future development that's been proposed, I think Steve Wilkes mentioned this on the last panel, is this possibility that an auction may determine the band plan. So sort of the ultimate in flexible use, where there's a chunk of spectrum and bidders could bid on unpaired blocks, bid on paired blocks, and the results of the auction could determine where that duplex split would occur. Is that something that operators are interested in the future, allowing market auction mechanisms to determine the band plan? Is that a realistic thing that we should be considering?
I think it makes it very challenging because I think one of the other panelists mentioned that you do have to have a downlink and an uplink, and as we talked about before, you don't know what the future holds in terms of applications and devices that will require more uplink. And so I think you need to think about, as an operator, if you're thinking about going in to acquire additional spectrum, you'd want to have some certainty in your business planning as to what those bandwidths are. Are they lined up with the standards? Somebody mentioned 5x5 as a minimum. I think wider bandwidths tend to be more efficient and more flexible, but there's also trade-offs there. I think if you leave it very, very flexible and unstructured, it becomes very hard to predict what the business model is, and therefore it's hard to develop a business strategy and plan around that.
Yeah, I think I agree with that. I also think we're open to smaller duplex gap. I think as long as it's technically feasible. As mentioned in panel 2, some of the issues in terms of our siting policies and co-location, those things are important that we all deal with together. So I think duplex gap could become smaller, but setting that as a rule set going into the auction and having the auction determine that, I guess would be difficult to plan for. Difficult to go into that auction that way.
I think first we'd have to find out what spectrum is available for that, and the size and the timing and all of that, and maybe that would help a little bit with the assessment. It's really hard to give sort of a blank answer. But if very little spectrum is available and it's a very tough spot, and maybe it's one thing. If it's sort of setting the future for all spectrum, and that's the way we're going to do business across the board, that's may take away some of the things that people on the panelists said earlier about some consistency is needed for devices. So I think it depends maybe is the right answer.
So, go ahead, George.
I was just going to add, I would agree, even though I'm an advocate of flexible use. I mean, too much of a good thing, right? But in addition, you always have adjacent services that you have to deal with as well, right? I mean, you've got to have some level of certainty there so that people know how to plan. And
well, maybe going the other way, if we were to auction paired spectrum, presumably for FDD use, is it reasonable for the FCC to declare one part of the band as the downlink band and the other part as the uplink band, or is it more desirable for us to leave that to you as to whether to use it for uplink, downlink, or even TDD, as is the case in, for example, the 700 megahertz band, and even the PCS band is structured that way, which is getting to this question of, is there such a thing as too much uncertainty? Is that a reasonable amount of certainty to add to an auction?
Yes, there is the potential for too much uncertainty. You really do want to define, if you're having an FDD block, which one is downlink, which one is uplink, so it's consistent across. If there's multiple blocks, they're all consistent, so you don't have operators in adjacent blocks doing different things and creating an interference boundary where there shouldn't have been one.
No, agreed.
Yeah, I agree. You probably want to think about grouping downlinks together and uplinks together so you can minimize some of the guard band and some of the other technical issues, and that way you get more value for the spectrum that you're thinking about auctioning as well, I think.
Absolutely.
Question?
Yeah, I was wondering, so at the beginning, at the start today, Marty Cooper talked about this spectrum roadmap idea. So thinking longer term, and Dan, you mentioned, I think you said something about preventing poor band planning, and you mentioned 700 megahertz. So are there things we can do? Would a spectrum roadmap help, and how would that come to pass if we did such a thing? And because one of the things we're doing in the TAC is looking at these multiband devices and the difficulty, everything you've heard today, of allocating spectrum that's coming in smaller and smaller chunks, or at least harder to deal with chunks. So I'm just curious what you guys think of like a spectrum roadmap kind of concept, or how we get the best ideas out there for us to follow.
Yeah, definitely. I think that's key. And I think the other thing, going back, just lessons learned from AWS, I think it'd be also helpful to have some more information on the adjacent entities, like the broadcasters. Like that was kind of a big question mark. Mm-hmm. And we had to go and work with broadcasters and really figure out what those issues were. Nobody had really addressed those issues. So any information that can be had on entities that operate, in blocks next to the band that is being auctioned is extremely helpful, and helps us put a valuation on the spectrum going in. If there's a lot of questions, I know, we all of us would probably be leery to put down, X number of dollars. And so the more certain the spectrum use appears to be, I think the more value the spectrum actually has.
Great. Well, thank you. Being told that we're running out of time, but I want to give everybody an opportunity to share with us some final thoughts on what we've heard today. I want to start with Tom.
Okay. Well, thank you very much again. Appreciate the opportunity. And as we think about future band planning, I want to thank the FCC and the TAC both for doing this, and thinking about flexibility, but also, a lot of operators utilizing currently FDD systems and utilizing those today. The asymmetric nature is something that'll be thought about in the future, but we also need to be thoughtful about the technologies we're operating today, because that's where we're creating revenue and so forth. And there's a roadmap certainly, but certainly practical solutions that we can implement over the next few years. A lot of the things that are talked about take a lot more time, energy to engineer, develop, implement, optimize than sometimes are understood. I think a lot of our suppliers and operators clearly understand that as you go through it. But and then it takes time for them also from the time they're initially implemented to become, they may be a little more niche solutions or so forth. So they're not necessarily a solution for everything. But I think having the options available to us will be helpful as we plan for the future.
Great. Yeah. Thank you for having me here. I really it's been a great day with lots of different ideas. definitely the idea of a spectrum roadmap of 5 to 10 years and where we should go, what spectrum bands would be available, and a plan for getting there would be very helpful. And otherwise, just thinking of new bands coming up, to the extent that they're clear of the amount of spectrum, what the neighbors are, what the use would be if it's FDD, which is downlink, which is uplink, and then ideally in relatively small blocks of 5 plus 5 megahertz. Many of the smaller operators in RCA have expressed interest in that as well.
Thank you for inviting us today. I think just the process you've taken that's very inclusive of suppliers and devices and very open, I think that will go a very long way helping us draft a plan and some more flexibility in it, given that very fast, rapid change of technology, an incremental approach that has a bit of boundaries around it so that we can end up where we need but allows us to begin to innovate in the short term. I think that would be very helpful.
Thank you.
Yes, thank you to the FCC for allowing us to provide comments today. Three areas I'd like to stress. One, global harmonization. I think that's key, and I'd ask that you consider that heavily in your decisions. Spectrum block size, as big as possible to allow flexibility, obviously. And third, I think the issue that Doug talked about, geographical contiguity, is a big deal. If you look back historically again at Clearwire, some of the biggest struggles we've had because of the way the band class 41 spectrum was allocated, we spent tons of money and time getting that aligned and in a form that's usable. So,
thank you. Dan?
Just thank you for your time. It's been a great day to learn a lot of information. It's been great. I think I would just reiterate some of the points I made. I think clearly FDD is the way we'd like to go, and the allocation of downlink and uplink clearly demarcated is important. Also, the AWS-3 pairing. I know that's not paired yet, but the 1755 plus is certainly a continuation of the AWS-1 band, which is important from the vendors' perspectives and also from our perspective. And as I mentioned, I think a minimum 5x5, if not larger, would be certainly beneficial to planning as we move forward with LTE. So thank you very much.
Great. Well, thank you to all of our panelists and to Brian for helping me moderate. And that concludes panel 3. Thank you.
Nice to meet you.
Good afternoon. I'm Julie Knapp, and I am the Chief of the Office of Engineering and Technology, and I'm the last speaker that stands before you're heading for the door, so I'll try to keep it short. Just try to keep in perspective that what this is really all about is providing access to spectrum for enabling the growth of broadband wireless services. And we, together with the NTIA, have been spending a lot of time identifying spectrum bands that could be made available for wireless broadband. We've talked about some of them today, whether it's 1755 or the spectrum that we recover from the incentive auction in the TV bands, 3550, et cetera. We're moving from the point of just identifying spectrum to start thinking seriously about, well, how do you use it in a way that makes it the most efficient and valuable access for these services, existing services to grow, new services to be introduced. We heard today about some of the things that need to be considered in developing the band plans for the spectrum. I couldn't help but think, Marty, from your remarks opening up the workshop about how much simpler it was for analog cellular. I mean, we had one band, we worried about out-of-band emissions, and we had a bit of spectrum to decide how to divide it in two. And today, the challenge, it's just a marvel what the equipment and the networks do today just in coping with all of the different bands that are available, and here we are looking to add more. We heard about the challenges that are brought about. Particularly, I think each band has its own unique circumstances. Need to think about things like the filter technology, the impact on antenna design, the block sizes, how much we devote to uplink versus downlink, et cetera, et cetera. And I think as you listen to all this today, it can seem really daunting. But I think on the other side, you've got technologies that have been introduced that are incredibly versatile and offer ways to make use of the spectrum that we didn't have years ago, where the technology might have done just one thing. Same thing for the filters. We heard about how the filter technology is getting better, how the antenna technology, even though we've got the challenge of 5 antennas and maybe more being in an individual device, how we're starting to move over time to SDR technology and the possibilities that that opens up. This brought back memories today for me of, it was at this point that the professor would say something like, okay, you've got a week to go off and design a band plan. Maybe we have a little more than a week, but the challenge for us is going to be in considering, and I don't mean just the commission, because I think everybody here is a participant in this process as we go forward, to take all this information and figure out how we get the right balance, the right mix. And I really want to thank everybody who participated, particularly the folks from the TAC, who Marty for kicking off with a great talk to get us started, for Brian Daly and Brian Mark Walter from the TAC, who helped co-moderate the panels. Also from the FCC team, Chris Halser, Tom Peters, Walter Johnson, Michael Ha, who also co-moderated, Celia and Smitty, who helped us organize, and can't thank you enough. We've got a lot to take in and think about. So have a great rest of the day. Thanks.